work together to make the 5G or any standard of 3GPP. It started from 2G and we were now in the 5G actually. So this is the governing body we all work. It's the body that constitute of the OEMs, means the vendors, the operators, carriers, the academicians. A lot of people participate here as a part of the member. And once we have stabilized what is 5Gs and the network, then we have gone through in detail what is a physical layer. And so the first starting point of any standard rollout starts with thought process that how this physical layer will be seen, actually will be visualized and will be realized. So the visualization part, the 3GPP normally defines it, and with its protocols and the framework actually. Now, some part they deliberately left out. That is what I will be covering here actually. And so the protocols and the base feature, the framework, what 3GPP from the layer 1 or the physical layer has been, I have gone through it. In the interest of time on that day, I was supposed to cover layer 2, but I brought the layer 2 here today. So today we'll see what is the layer 2, where it stands actually in the overall gamut of the whole 5G network. And we'll introduce the layer 3 here. So what is our layer 3, how we different from the typical OSI layer, and how the radio access, this is nothing but what we call, somebody we call as a base station, somebody as a terminology of 3G we call the G node. A lot of things we have defined. So we'll see that how the radio access network looks like. And we'll stop at that point and we'll go over to the core network, because this is the biggest part of the whole network deployment from the complexity point of view. You'll see that how I unfold the complexity over there. And we'll try to see that cover the call flow. Like for example, what happens in the background actually, moment we don't realize the complexity unless we see it is very easy that we just click our phones, we start our YouTube session streaming, we start our voice call. But there are so many things happens in just
Saptarishi sir, your voice is going high and low quite often. Can you please check?
Okay, then let me rejoin once, or I don't know. Okay, just a sec.
Saptarishi sir, can you hear me?
Is it clear now? Better or?
So it's going on and off.
Okay.
I don't know whether
Maybe the Wi-Fi is.
problem is at your end or my end. How about others? Can anybody respond in the chat, please?
It is going up and down.
The audio is
volume
breaking
going
for
up and down,
everybody.
man. Yeah, I'm also feel that, but it is kind of okay. I mean, I was able to follow what he's talking, but it is going up and down. You are right.
Hello, participants. Can few of you respond whether the audio is fine or it is breaking? In the 5 minutes, there was a lot of breaks.
Madam, sometimes it is good, sometimes it is feeble, but it is okay. We can hear.
Yeah, this Dilip. I think it's okay.
Sir, you can continue, sir.
Yeah.
Okay, let me just
try to keep the mic closer to you and speak.
Yeah.
It's going very feeble sometimes.
Okay. So now we'll put forward what is there in the core network actually. So this is the one of the biggest aggregator point of the 3GPP any domain, whether it started from 2G, 3G, 4G, or 5G. So the core network plays a biggest role in deploying a network actually of this gamut, because radio access is, you will see, is one aspect of it. But the core network is what we call as the final aggregation point of a network. I will then try to go into the call flow. That here I want to just project that when you try to browse or try to stream or try to talk, there are a lot of things that happens in the background, and so complex that it's so many entities we call actually, and the entities with respect to the device, the base station, the some of the core network entities here all participate to make sure that a packet successfully get delivered from the internet towards the phone, and vice versa from the phone back to the internet server actually. So a lot of things happens. I'll try to talk about the first part, that how a mobile actually get into the system, into the network. And it's pretty complex procedure actually, though sometimes it looks very simple when I draw the flow over there. But it is so many complex things that happens that every entity has to be synchronized, not from the clock point of view, the messages and its error scenarios it has to go through. It has to be harmonized and synchronized to make sure that the signaling happens fine, then the packet gets successfully delivered. So some part I will cover today, and some of the majority part I will leave it to in the third last day of it. And there we'll see that how the handover happens, and how the actual packet flow happens actually from the internet, vice versa, what I talked about. After that, I will spend more time in, this is where the algorithms that I will try to give a glimpse of it. And this is the secret sauce of any vendor's products that get into this 5G network. So vendors doesn't reveal what the algorithms are, in the sense they are mostly of the patents that we all research, what we call as do the product research actually. And we try to differentiate and keep the best algorithms for differentiating our products. And 3GPP allows that vacancy to be deliberately to be there actually. So here the innovation starts, and the innovation is spanned across both in the physical layer, both from the layer 2, both from the layer 3, both from the quality of service. A lot of places that you will see that how the algorithms, I'll give the glimpse of it today, but some of the little bit of the mathematical aspect of it, I'll take up on the day 3. This is the another big aspect that will give a little bit of different flavor that we all talk about. Okay. So I'll jump toward it. I'll not go through the details. This is the day 2. We'll start off the layer 1 unfinished story of the layer 2, and the layer 3 I'll jump into it. So what we covered is a lot of things you can see in the slides I don't want to get into, but this is what the summary on the day 1 I talked about, that the deployment, the headnet deployment, the cross-haul deployment, the split function of the 3GPP. And we gone to the physical layer with respect to the spectrum bandwidth. That is what we call as a waveform generation actually. So this is the waveform that we have modified keeping in 4G as a base. But the whole thing's got revamped actually from the waveform 5G waveform point of view. A lot of things that we added, a lot of new features I have covered in the day 1 itself. And what are the physical channel and reference? So today we'll see the next gamut actually, that this is the base architecture or the deployment. I just give a snapshot here. I'll not explain in details, but we are here now. That is what we call as the base station or the radio access network, different terminology we call them. And this is what we have covered in the day 1, the physical layer aspect of it. Now we are going into the day 2 today. We'll see that normally the layer 2, when we call, these are the 3 big layers that the 3GPP defines as a part of the layer 2 communication. So typically in vis-a-vis, if you see the OSI part of it, in 3GPP, we normally devise from layer 1 to layer 3. This is the way we normally differentiate our things. And most of the OSI's functionality are somehow been distributed, but in a different names actually. But you will see that same functionality are being repeated. If you are able to recollect the base theory, you'll see so a lot of things are already covered in and splitted across these 3 part of it. Now the question that normally happens here is that why so many, we call as a layer 2, but these are all protocol by itself actually. These are all heavyweight protocols that takes some aspect of it, because just imagine that 5G didn't come just like that actually. It is a precursor that it started with this 2G, and slowly bit by bit we added everything, and now we are standing at the 5G. So these things came at a certain rollout scenarios that what we felt that is needed. Then only we started adding and more complexity to it. Actually, that's the way the things get evolved and complex. So a lot of old stuff we have discarded, a lot of new stuff we have added into now, and a lot of modification we did it. We thought that this is not relevant because of the use cases. And based on the 5G use cases where I talked about that, we are talking about enhanced broadband or the high reliable services, low latency into it, massive IoT into the deployment scenarios. So each of these things, the complexity has been taken out from the older architecture. And based on that, we have kept it, these three architecture. We'll see that how these three things play a majority role. Now, this is what we call as a protocol. What is a protocol means? There is a handshake defined by the 3GPP actually. So we cannot write anything beyond this sky actually, because we have to take this 3GPP into consideration to make the base of the base station or the device or the core network entities to work, function. So that is your base actually. If base means we can talk to a base station with any phone. A base station can talk to any core network entities actually. So that's the way the base has to be there. And the base governs the way we handshake to each other. Like for example, if the UE or the user equipment wants to talk to a base station, it has to have to implement these protocols to communicate to the base station. Without that, he's out from the network itself. So this is the governing principle that the any of this 3GPP or any standard follows actually. And it's a peer-to-peer. It means that wherever you find one protocol entity, normally we try to find out where its other peer residing to. So suppose we take a base station. So we say that, okay, there is a protocol entity called SDAP, there is a PDCP, RLC MAC, Phi. So where is this equivalent peer residing into? So if it is a base station and it's talking into the wireless aspect of it, so obviously the user equipment is the person where we'll try to find his peer entity. So you can see that arrow goes like this actually. So peer-to-peer talks. And whenever a peer makes a packet, so this is a packet, the packet goes to the next peer, we add a header and take the old packet here, then this guy will add another header. So like that, it goes out to the air like this. And it goes back to the physical layer. It starts stripping out the headers and one by one, so that every layer gets its own unit, data unit actually. Whether it's a signaling or it's a data, doesn't matter to it. So this is the way it has been devised actually in our network. So today when we say a layer 2, I'm still standing in the base station side, and I'll try to cover that what is layer 2. So what is the protocol, why it is needed, and there are a lot of software engineering happens here, because we need to implement this layer 2. It's from the standard, we read the standard, we do the software design, we make sure that, okay, I have an equivalent real 5G phone to interwork. So what I need to enable, configure, a lot of things that goes in the background to make it happen, apart from the algorithm. Algorithm is separate, I'll come to that. So this is the first aspect of it. Now, the starting point is the physical layer. We talked in details. This is the layer 2 we'll cover now. This is what we call as the layer 3. The two big aspects of the layer 3. One resides in the base station aspect of it, and its equivalent reside in the user equipment. And what is the third layer 3 component called the non-access stratum? You can see that its arrow straight away goes to the AMF of the core network. Now the question is why? So the big question that we'll try to answer, that there is one bypass happened. The base station doesn't sneak into the packet of NAS, and straight away it has been transported back to the core network for a big reason for that. We'll try to uncover the big reason why we do it. And this is what we call as the control plane actually. Now I told last time also that before we do anything, before we invoke any of the stuff, the data plane, what we call as a user plane, that is nothing but your actual YouTube data goes or streaming or voice goes, we have to ensure that this control plane is successfully able to talk to each other. Like RRC from the device talks to the RRC of the base station. The NAS of the UE talks to the NAS that is residing in the core network. The PDCP like this, they have to talk to each other to ensure the control plane is up and running actually first. Then only the data will start flowing actually. Now you can see the names point of view that I see the control plane also has a PDCP, but if you see the data plane also has a PDCP into it. So there is a layer 2, and here also I'm calling the layer 2. Now why? Now the question is that this part is now agnostic whether what is there coming from the top and below actually. So that this layer 2 is become like my transport actually. So it gives the services that whether it is a signaling or whether it's a packet that is carrying my YouTube via like this, is irrespective of it, it has to be taken care. It has to service any of that sort, whether it's a YouTube or whether it's a signaling data that the device wants to talk to the network for doing some handover signaling or something. It has to go through this layer 2 transport actually. Similarly, if it is a YouTube data that he wants to send it to the network, receive from the network, or send some FTP file he wants to upload to the network, still he has to take this layer 2 services actually. So this is the governing principle, that the layer 2 doesn't worry that what is coming from the top actually. Now that creates another big problem. What is the problem? We'll talk that. Just keep in mind that layer 2 has a problem that he has to know, or he doesn't want to know, that what is coming from the top actually. Top means this is what we call as a layer 3 signaling packet, or it's a layer 3 data actually. Now this is the fallacy we'll try to uncover in the next couple of slides. Now let's see what the first layer, if you see now we are here, that's the guy called the medium access control talking to the physical layer actually. So this is where we'll see that how this MAC is actually playing his role actually. Now, what is the main entity that he's bothered about? So I talked about he's bothered about transferring the data, because any layer 2 services is meant for the data. That is for sure. That's the thumb rule. Now, what top of it does it, you will see all this entities called logical to the transport I talked about. Because a layer 2 is actually a transport mechanism. So in that transport mechanism, he tries to do a lot of innovative algorithms that we'll talk about in a snapshot, a couple of slides later. So he does this, the mapping. It means that he understands that what is the logical entity that is coming from its top. He does the multiplexing in the sense like, remember all the 3GPP, we follow the multiple access actually. They're all multiple access schemes actually. Now, unless I multiplex, so my base thinks it doesn't mean that one mobile, one base station. It doesn't go in that order. So if it doesn't go in that order, then what happens is that this MAC entity does the final multiplexing of it. This is where the multiplexing scheme get defined actually. So whatever the entities that you want to talk about for different mobiles handling from the base station perspective, it has to multiplex. That's where the multiple access starts coming in the MAC layer entity itself. And if in the other side, if somebody does the multiplexing, then I have to do the demultiplexing from the device. Suppose the base station does the multiplexing and send the data out, then the MAC will do the demultiplexing. Keeping in mind, I will not demultiplex somebody's other user's data packet. We try to protect in a different ways actually. Then it does what is called the biggest important things is the scheduler actually. And from the GPRS days till now, till 5G, this innovation is thousands and thousands of paper has been seen it. A lot of PhDs has churned out their entities just focusing on this entity called the scheduler actually. Okay. Now, another things that we added is that how successfully, now if you go back to the OSI's part of it, the forward error correction that already happens in the channel coding point of view in the physical layer. Now then why we started putting the error correction mechanism in the using form of what we call as a hybrid automatic repeat request actually. So this gives another flexibility because physical layer does one respect of channel coding, and if the channel decoding fails, it tries to discard that bit stream actually that has been sent. Now, who is the guy who will ensure that, okay, let me do the second repeat actually, the third repeat, fourth repeat. So what we did from the 4G days onwards, we thought that the fast retransmission schemes where the Mac is closely working with the physical layer has to implement the error coding scheme actually. It's not a coding scheme point of view, but he takes the control of doing the repetition actually, triggering the repetition. So that is the biggest entity that we have called with a hybrid ARQ. And one part of the ARQ is already, I'll show you, is already there. But the Mac does the second level of the fast retransmission scheme actually. So it triggers the physical layer that please start the second retransmission if the Mac sees that the first transmission was an erroneous reported by physical layer. So he does some magic over there, try to think that, okay, let me change some of the redundancy protocol, something like that. And let me trigger the second retransmission, third retransmission, up to some nth retransmission that what has been configured from the standard actually. Because we cannot go and keep on repeating if the mobile is in the very bad channel conditions. Then after nth retransmission also, if you're not able to make sure that the packet has been successfully delivered to the device, there is no point. We have to abort it actually. So it means that what we call as a packet loss actually. So the Mac actually tries to cover this packet loss schemes. And based on that, the scheduler wakes up and does some other magic actually. So this is the overall gamut actually, that there are a lot of functionality that Mac layer, and steadily every standard or every release from 2G, 3G to the 4G, whenever this internet starts came from the GPRS onwards, the Mac has grown tremendously rather than any of the other layers actually of the layer 2. Because every standard, we are adding more and more functionality to this Mac itself. And Mac and Phi has become very hot topic for any research schemes going forward actually. Okay. Now, this Mac cannot work alone in the system actually. It needs a lot of feedbacks, a lot of things from the device, from the physical layer itself. So that is where we see that what we call that Mac needs services from the physical layer to do his job actually. So it is not very independent entity. Like physical layer, if you configure, he can do his job. But the Mac is the guy who actually governs what we call as from the data plane point of view. He tries to get the feedback from the top, from the bottom is the physical layer, from the device. Everywhere he'll try to get his feedback. And then he does his job actually. So that's the reason that in the data plane, in today's world, and in the 4G, 3G, 4G, in anywhere if you take and try to compare, the Mac has grown tremendously actually. So this is what the base function of the Mac itself. Now, Mac doesn't stop there actually. Now, what we added top of this Mac is that we have added the random access mechanism. I'll show you when we deal with the RACH in the day 3, the maths aspect of it. But the physical layer who gets into the random access, but the procedure of RACH is not complete unless Mac comes actually. So now you can think that how he plays the first role then to make this mobile get access to the network is via this random access scheme. And he plays the first big role to ensure that the RACH scheme procedure is successful actually. Okay, now he plays a big scheme in the data transfer, both uplink or the downlink, doesn't matter. This is where he plays the biggest role in the uplink data transfer and the downlink data transfer. And he plays a big role in what we call scheduling requests. Like, for example, the MAC of the device has a packet. Like, for example, you want to send, you want to upload one picture to Instagram, actually. So it's like uplink data has to be transferred. But the base station doesn't know when you want to upload the picture. He's clueless, because now how to make the base station aware that now it's a time for me to send or receive something from the device. So this is where the device wakes up and the MAC of the device starts sending the scheduling request, and the MAC comes in giving the grant, actually saying that, okay, I grant you the mechanism now to start putting or send the picture to the internet server, actually. So this is where again the MAC's help is required, actually, not the fine. MAC comes into, wakes up into it. MAC also plays a big role in doing the discontinuous reception, actually. So it means that whenever we want to go into power saving mode, MAC's help is needed. MAC's help is needed also doing what we call voice over radio or voice over NR or voice over LT. So this is where we give a dedicated, remember, from 3G onwards, we all migrated towards the IP packet domain. So whenever it's IP packet, there is nothing called the circuit switch network is gone, actually. So in the packet switch network, whatever the voice you are seeing now has to be embedded to it. So in that packet switch network, if I want to send voice, I need very persistent scheduling scheme, actually. And again, we take the MAC services by the scheduler to do it. So MAC also come in rescue for doing the paging, doing the broadcast. Now you can see that how big is this entity list that the MAC takes care. And all this scheme has been culminated and been governed by this entity called the scheduler. So that's the fundamental of the MAC. Now let's see what it does. Just I have summarized in very short way, actually. And in the day 3, will this expand to the fullest extent to it, actually. Now you can see whatever I have written to it, that the scheduler controls. Where is the scheduler line? That is in the layer 2, actually. So layer 2 has first part called the MAC, and the MAC has 2 entities here. One is the 3GPP defined protocol, actually. So this is where we have to abide with it, because I told you without the protocol, I cannot talk to the device. Base station cannot talk to the device, and device cannot talk to the base station. So MAC to MAC communication is needed. But there is an entity that is missed out deliberately by the 3GPP. And this is the entity that is been talked about and researched with the fullest extent, actually. So he does all these services. Just imagine, I talked about this kind of layers in my physical layer. So he is the guy who controls the synchronization. He is the guy who controls the control channel, which tells the physical layer the time to send the control packet, time to send the data packet in the downlink, in the uplink, U for the uplink, D for the downlink of your channel. Time to track the sounding of the channel response. Time to take care of the feedback from the device aspect of it. Device whose channel has been sounded, the MAC gets the report. The MAC is worried about the mixed numerology I talked about. What is numerology means? That we talk about mu0, that is nothing but my 20 megahertz bandwidth aspect of it with the 15 kilohertz SCS. So like that, we have mu1, mu2, mu3, like this, we have defined it. So each of this numerology has its channel bandwidth and its subcarrier spacing to it, associated to it. Now the MAC is the guy who does the resource management of this numerology. The MAC is the person who does the scheduler, mini slot, the bandwidth division. But once we divide the bandwidth, maintaining the bandwidth, what to go in which bandwidth, the MAC scheduler start into it. So you can see that these are the big entities in this part of the scheduler who works as a global purview in the scheduling domain itself. So he controls the multi-layer transmission. He decides when to do the multi-user transmission. He controls do the digital beamforming. He controls the carrier aggregation. Means that when we invoke simultaneously two carrier towards the device, or 3 carriers or 4 carriers, when to invoke the question mark, when. So the scheduler comes into that part itself. He controls the power control, slicing, RLF, radio link, the TDD reconfiguration. Now you can see that how big is the entity. Just a small name called Mac is doing it. So this entity, what we question mark, has actually bubbled from the GPRS days back to the 5G days actually. Because every time we add up an entity, a feature, these are all features that the 5G has offered. So where we put his residing factor to control, we go back to the scheduler and say that, hey, please accommodate the new feature called the mini slot of the URLCC, that ultra low latency, high reliable communication. So everywhere we go back to the scheduler and we enhance the scheduler, and this is the biggest algorithm that controls the complete data plane actually of the whole 5G network in the radio level actually. So this is the heart of the control system, where the physical layer abides by the rules set by the scheduler. He obeys the command configuration given by the scheduler, and he does the job actually. And the vice versa. So the scheduler resides in the base station actually, or what we call as the RAN or the G node tree actually. So there is nothing called the scheduler per se in the device, but they have done some bit of something. I'll talk about a little bit of the part what the controller MAC control layer in the device aspect of it. But this is the entity that the base station that normally governs the first layer 2 beyond protocol, what we call as the scheduling algorithm actually. So scheduling, when we started, doesn't mean scheduling a packet. It is the first aspect of it. But it is more that you can see the bullet points, and more we are adding up. The more bullets are getting added up because of the more features that we are adding as the release of 5G is going on. Okay. So this is, I will cover in the day 3 actually, that how we actually try to give a snapshot view that how a scheduler is designed actually. Okay. So how we actually takes care of this one actually? What is the mechanism? So we'll wait for the day 3 part of it for this scheduler design, where I'll also uncover the physical algorithm and also uncover the scheduler algorithm per se actually. Okay. Then we come to the next part of it. If you just see the hierarchy I'm moving now, this is the physical layer that is there. Then we have the MAC, and the MAC has 2 aspects. One is the protocol aspect and the algorithm aspect. Then the top is your RLC guy actually. So this is called the radio link, but it does couple of 2 significant aspect of it. What it does, this is the person who does the first part called the segmentation of the packet actually. Now, why we require the segmentation? Because the R of RLC is the radio, and the radio has the limited capacity to transmit. So it doesn't mean that whatever the base station is there, he gives every of the radio resources, that is nothing but my OFDM resources, to one single EV. That is inefficient transmission scheme. Then you are devoid what we call as the multiple access actually. So if I want to do the multiple access, so I have to break the packet from coming from the top. I have another entity called PTCP as a part of the layer 2, but this is the final guy who does the breaking of the packet. So he breaks the packet. So if there is a packet, there is the bits are there. So again, this person will tell that please break the packet. So suppose this is 100 bytes of packet that the RLC is having it. So MAC will tell that give me only 10 bytes at time t is equal to 0. Give me 25 bytes at t equal to 1. Give me 50 bytes at t is equal to 2. So in time series manner, actually, this. So how to break the packet is again governed by the MAC, by the scheduler. And the RLC follows the rule of doing the segmentation of the packets. And obviously, if the base station segments the packet, so now you can see in this scheme that 10 bytes goes, 25 bytes goes, 50 bytes goes. To consider 100 bytes from the G node B, if this goes in this order, the 10 bytes, then somebody has to accumulate. So that the person in the device, the UE's RLC, will start doing the reassembly, what we call. So 110 plus 25 plus 50, like that. So finally, he'll form the 100 bytes to the device. So this is where the segmentation, if at all, it does in both the side, the G node B or in the UV also, we can tell to do the segmentation. So the other side will do the reassembly. So this goes in hand. But another important things that happens here, two important things. The first things that I have written are called acknowledged and unacknowledged mode. Now, if you go back to our old days of OSI part of it, so you find little similarity. What similarity? That if you go back to our TCP and UDP, you may find some similarity here. And that exactly what we call as acknowledged and unacknowledged mode, actually. So if you go back to our OSI days of the UDP packet, so it is a singular direction packet. We don't wait for the acknowledgement that whether the peer entity, the client server, if there is a client here, our server sends an UDP packet to the client. So whether server is not bothered whether this UDP packet has successfully received or not, actually. It doesn't bother, because that's the way the UDP protocol has been designed. In the TCP, it's acknowledge mode. I need to have acknowledge, and then only I'll send the next, and that's the way I have the TCP congestion control kicking in, actually. Now, exactly the same rule has been followed here. So unacknowledged and acknowledged is where the RLC takes out that certain packets that needs acknowledgement. The RLC actually is the person who monitors it, actually. So it means that he waits if the base station sends an AIM packet, acknowledge mode configured packet to the device. Device has to respond with that, hey, I have received it. Then only the next packet will be sent. Now, if till the point the device doesn't tell that I have received the negative acknowledgement of that, then RLC keeps on doing what we call as an automatic repeat request. It is called ARQ, not hybrid. Okay, hybrid is done by the MAC guy. So this is the kind of similarity between what RLC is equal to my TCP and is with respect to my UDP. It's like an analogy we are trying to draw here, but it goes in that order that for certain scenario of packet, we really don't bother that I need an acknowledgement. So why I want to do the overhead of getting a feedback, because that also have to take into control, actually. So this is the biggest things of managing the acknowledgement and unacknowledged packet, and RLC is the person who does that aspect of it. Now coming back, it's called another important called sequence and the duplicate detection, actually. Now these are the two important things in the wireless. How we know, suppose I have told you that this is 100 bytes from the MAC. Now the total packet is done, 100 bytes is maintained by the RLC. Now, when something might happen, because this is a wireless, actually. So the base station who is sending this packet from the RLC layer, it will be received by the RLC in multiple times also. So means that EV may receive duplicate packets from duplicate paths. So same physical doesn't know it. He will forward to MAC and MAC will forward to the RLC. So he may receive the same 100 bytes twice in the system, actually. So who maintains that these are all my duplicate packets, actually I'm receiving it. So this is where in the wireless we do the sequencing numbering part of it. And we ensure that the sequence has been maintained. Like we give a sequence number 1 of this, say this is my sequence number 1 of this 100 bytes. Another sequence 2, sequence 3, like this we can do the sequencing. And the sequence number is matched in the either side, because if mobile sends, the sequencing will be matched and duplicate detection will be happened by the base station, and vice versa. If base station wants to send the sequence packet, the duplicate detection will be maintained by the RLC of the device itself. So this is important to happen because finally it's a single packet with respect to the IP domain actually. Okay. So when we come to the IP world, though the IP packet that is coming, it is a single packet to be treated from the end application domain of the end application domain, whether the application termination happens in the device or vice versa in the internet. I cannot send same packet twice to the application. It means that just imagine I'm saying hello, hello, hello 3 times because I've received 3 such duplicate packet, and if RLC was not doing my duplicate detection, so deliberately with single transmission of hello, the other application layer will get 3 hello, hello packets. Okay, that is not good actually. So this is where we call that one entity has to do the duplicate detection, and duplicate detection is done, and we put this entity in the RLC layer itself. So it's very small, thin layer, but it caters to one big entity in our the complete layer 2 aspect of it. So it does the sequencing, segmentation, reassembly, and duplicate detection aspect of it. Actually, these are the 3 big entities. Plus, there are sub aspect of it, what we call the ARQ aspect of it. This is what initially we thought that RLC will do the error correction by repetition. Remember, it is not a forward error correction that the physical layer does it. So it will do the repetition of the packet. It takes the control. But now we have added the HARC in the MAC itself. So both these 2 guys, you can see that how many times we have put 2 checks, one in the MAC layer, who does the hybrid ARQ for the same repetition, and also from the RLC level repetition. Now, what is the difference? Let me give an example. I give an example called 100 bytes. So 100 bytes MAC scheduler want only 10 bytes of the packet to be sent to the EV. Now, suppose EV doesn't get this packet, he will send a negative acknowledgement actually. So then the scheduler will kicks in and sends the 10 bytes, maybe 1 time, 2 time, 3 time. So this is nothing but 10 bytes is getting repeatedly. And this is governed by the scheduler, by the MAC, under the MAC purview. Now, like that, if at all these things is not been received successfully, what happens? Now, this is discarded. Okay. Now, just imagine where is my source packet line? That is still my 100 bytes here. So what will happen to the RLC? So RLC never got this 10 byte, but he might get 20 bytes. He may get 50 bytes as per my algorithm, but this is the vacancy he's having it. Now RLC will immediately know that there is a vacancy and he will start doing the ARQ mechanism. So because I need 100 bytes successfully delivered. Now, if at all ARQ fails, then nothing can be done because we can just leave that and send it out to the other side of the application layer. And whether he with his source decoding, if he want to accept and want to render the packet, he may do it or he may also discard it. So it means that both the side, RLC and MAC, has done its best to transmit the packet in multiple times. That is what the error correction from the RLC point of view. Now, in 5G, we added another protocol, a layer called SDAP actually. Very small, another thin layer. And this is what the flaw that we have seen in the 4G world actually. And this is the big thing that we all talk about in the base station, that, hey, how best is your base station is able to maintain the quality of service. So this is the entity that we thought is that to be more aware of the quality of service with respect to the another entity called the data radio bearer. I told you data means immediately if you strike out this YouTube data or voice or whatever. Radio means it has to go to the radio, and bearer means that it has to be transferred through some mechanism. So now the question is that I have given you a pipe. This is my pipe of transfer in the air interface, including air interface. Now in this air interface, if I want to transfer a packet, initially what in the 4G world, what we used to do, you just take that packet and just put it to the scheduler. And the scheduler will do something, and whether it's successful, then it's a scheduler job to maintain it. Then the scheduler is sometimes also helpless to do that transmission, because this is coming from the top, because I didn't put a signature that is this a packet of high relevance that needs a little bit of QS enhancement. That has to come to that, or it doesn't need actually. So this is where the control layer has to be aware of it, saying that, okay, some of these packets also has to be treated differently. That is where we added a new protocol called SDAP actually, where it does the QS mapping on this pipe. Think of this is my data bearer pipe. And he adds our entity flag, what we call as the mapping between the marking with respect to flow indicator actually. So I just ensure that one flag is checked and some indicator flag is checked. That will help my system to perform actually. And this is where the entity, the SDAP, does what we call as the flow control actually. Because what is happening till now in the 4G, we just send the packet. But the scheduler is also a bottleneck actually. So if I don't do the flow control with respect to this SDAP, this scheduler is getting bombarded with all varieties of data packet. But with this SDAP, a little bit of the flow control, I can easily manage the congestion control at the schedule itself. And that is where with just a flag, with respect to the marking, I able to control this entity of the flow control actually. So this is a new part of the things that we have added up, just to ensure that my quality of service is maintained, though it was maintaining through the scheduler. But now what is happening is that with respect to all the different varieties of the services that the 5G is defining, and I need to make the scheduler be little bit of work in a congestion less way actually. Because whatever invent we do it in the algorithm, any algorithm has its bound limit actually. So within this bound limit, I cannot go stretch it out here and here, because I don't have a supercomputer in the base station that takes care of all this stuff actually. If I had, then finally this is not there. But with respect to the bound limit comes with respect to the hardware, with respect to the operating system, a lot of things are there that the algo should aware of, that which hardware I'm working. What is the things? These are all software engineering also get added to the algorithm, because else if you just write a maths and put it, it will be just blow up actually, and nothing will go actually. So these are the certain things that we thought that better congestion management, let's add up this layer to do it, to help the scheduler lesser his burden actually. I moved to the last layer of the layer 2. It's called the PTCP layer. And this PTCP layer does another big entity. And the first big entity, what we call as the header compression, I talked about. And this is very much is needed in our things, because normally what happens, we have this IP headers, because remember, any of these internet packets has the IP and header into it actually. Now this header has its own size, and the size matters when this, if I don't compress it, if I don't compress, it will take a lot of radio resource also. But this is essential, but because I have a payload here, so I cannot compress this payload, because if I want to compress this payload, it becomes a lossy compression, and retrieving it will become a difficult task. So that's the reason we need to ensure that the payload is not compressed, but whatever I can compress, we took it the compression mechanism from the IETF vault actually. And we use this IP header compression is one part of it. The another biggest thing that we do is what we call as a ciphering actually. This is where the complete ciphering and the integrity protection This is governed by the 3GPP mechanism actually. So what is called integrity protection and ciphering? Ciphering happens on your data packet and integrity protection happens on your signaling packet. So this is the thing that the PDCP, this part plays a biggest role in doing this two big job of our transmission, the ciphering, integrity protection, the header compression. And plus we have kept it another check called duplicate detection, packet in order delivery, because this is the last part from the PDCP. It enters to the wireline world. Wireline world actually means the Ethernet world actually. So if it is uplink from the device, it goes to the base station, and from where it enters the Ethernet world actually, and before it hits to the internet. So that we also put this duplicate detection, reordering everything, whatever you see some part in the RLC aspect of it, same thing has been copied here, but in a different form factor. But this is the two-phase big aspect of the PDCP who completes now the complete mechanism of the layer 2. Now you can see that a lot of times we have kept it a little bit of RLC has some job, it's again getting duplicated by the PDCP because to make some redundancy actually, because if I don't do it, you may, because beyond this, it is out of our control. This packet out from the PDCP world, it just goes out to the Ethernet world actually. After that, we don't have any control anywhere actually of the system. So this is where the PDCP ends, and here there is no algorithm per se. So it is not governed by any algorithm. It is a simple 3GPP protocols that we need to start doing our implementation. It's purely a software engineering and the implementation aspect of it. But this implementation also has to be governed by the what 3GPP standards tells actually. So we have to read the standard, understand how it has to be done, and then we normally implement the PDCP protocol. Let's say where the SDAP aspect of it, some bit of congestion control, flow control, we also do it, but not as a gamut with respect to the MAC, where at least 80% or 90% are all scheduler, and only 10-20% are the protocol entity by 3GPP. So all in all, when we say a layer 2, and so layer 2 of our in the base station and vis-a-vis in the EV and in the G node B. So our layer 2 has this MAC and this RLC and this PDCP actually. So this is our domain of layer 2, what we call, and top of that we add SDAP part of it to augment the functionality for our layer 2 aspect of it. Now I move into the heart of the base station. That is where we call the radio resource controller actually. Now this is the heart of the whole base station. When you say a base station, a radio access part of it, so it has its physical layer, it has its layer 2, the 3 entity PDCP, RLC, MAC, and SDAP. But the person who controls everything, to everything, even to the device, is nothing but this guy called radio resource controller. Now again, it has the bigger aspect of it because it manages the broadcast, what to be sent actually. So it means that content actually. Because if this content is wrong, then we know the implication what will happen actually. So this is the person who established the radio connection actually. Okay, with respect to the device, the connection between the device and the network. And this is where you can see here the RRC of the user is just a slave of the RRC of the base station. This is the heart of it. So whatever the RRC of the base station will tell to the RRC of the device, and this device internally configures its own part of it. So if we not able to do it proper job here, then the device will never ever come back to the network anytime soon actually. So this is the part of it, the controller aspect of it. Now, how much of algorithm and how much of configuration, it's 50-50. Okay, we'll come to that actually. Because when I'm talking here, RRC also has the two part of it. One is the pure protocol aspect and one is the algorithm aspect of it. So the algorithm will come next actually, but the protocol is where it establishes the logical connection between the entity. I told you everybody is a logical entity. So RRC of the base station has a logical connection to the RRC of the device. And the base station initiates it actually, that how things will be done actually. And sometimes the initiation happens here, sometimes the other procedure initiation happens here. So whatever, if the mobile initiates, this is the master actually. So the master takes into cognizant of a lot of things that the operator wants him to do actually. So based on that, he accepts, he rejects, he does whatever, he reconfigures whatever he wants to do actually, he will do it actually. So this is the biggest aspect of it, that unless we establish a logical connection, we not able to communicate anything here. Nothing will go actually. This whole thing is broken actually. Okay. So it means that to make it happen, the RRC is a part of what we call as the entity of the first layer 3 connection. And it has the entity here in the device to establish a logical connection with respect to the device and the base station. Both are in tandem. And then only we can do the other procedures per se actually. So this is required when you start your sessions actually. What is session? I'll come to that. Now, unless this is done, nothing will go from the top either side actually. And the biggest algorithm that happens, I'll come to that, is called the mobility. And this is where the handovers and all the stuff is been residing. And this is where the heart of the quality of service management, like the congestion control from the radio network and all the stuff. These are all things has been governed by the RRC, what we call the algorithm aspect of it. Okay, so sometimes we call RRC as a protocol entity, and we normally segregate the algorithm in a different form factor that I'll talk, but it's just a nomenclature aspect of it. A lot of people make RRC and the algorithm as a single entity. Sometimes people say it is a different, it is all the way you see the world actually. So this is the way the protocol entity ensures that these algorithms is working to the fullest extent. Because first, if there is no connection established between these two logical entities from RRC to RRC, nothing will go, nothing will ensure, nothing will happen actually. That is first aspect of it. Now, one thing that RRC does a little different, that will come with the broadcast aspect of it. So what to be broadcast, that is very important decision actually, because I talked about the broadcast is the where the device eagerly waits for the network to get configured. Okay, so without a broadcast channel, what we call, the device doesn't know anything of the network. So RRC plays a big role there to tell a lot of things with respect to what we call as the timers, counters, what is the handover thresholds, a lot of things we tell to the device actually. So that has to go prior to it before we do any data transfer. First, the device has to be configured, because device is a slave. He wakes up, he got synchronized, just got synchronized, but he doesn't know what is the configuration that the operator wants him to be aware of it. Now, which is the person who makes him aware? It is nothing but the RRC of the base station makes the device aware that the handover thresholds that you need to monitor is so and so. Then only that handover events will get triggered. I'll come to that. So these are the first fundamental entity. And after that, then for the data, when both the sides wants to do any data transfer, so the logical connection has to be established and has to be maintained till your the data is done or you think that it is complete actually. So that's the way it happens. Now another green entity I have kept it here. So this is called the non-access stratum, and this is the heart of the device layer 3, and that get terminated to one of the entity called AMF, access mechanism, that in the core network actually. So here base station doesn't play any role. So, but the base station just becomes a relay actually. It doesn't sneak into the NAS packet and transparently send it to the core network. Now for what actually? Now, if you just see now, because slowly we have to uncover the importance of this called core network entity. So steadily you will now see that the rather than the base station, this green entity is actually the top master. Slowly you'll see that, and we'll see that okay how the radio network or the base station mellows down to the guy called the NAS actually, because this is the person who does the initiate the cell search, and then when you switch on your device, the NAS software wakes up and tells the physical layer that please start the cell search mechanism actually. So after the cell search mechanism is done, it will trigger the device RRC to do something. So this is the nothing but the actual mechanism from the device's world, the non-access stratum who starts the registration process with the core network actually. So it does the authentication of it. It means that that's the biggest entity called the authentication. Like we in 3GPP, we don't allow any device just like that get into the network actually. So there is a big procedure goes in doing the authentication actually. A lot of this challenge happens from the core network entity to the device, and he has to do the challenge response. Some mechanisms are there. And once this authentication is complete, then only the next entity starts where I wake up the RRC to does the PDU session. This is nothing but what is I'll talk about what this PDU session means. Maintaining the quality of service, maintaining the slicing, everything. So now you see that when you say a layer 3, the layer 3 base station also has to mellow down, because before we wake up, a lot of things happens actually, in the sense like, though RRC becomes a transparent entity, he doesn't sneak into it. He does do the service part of it with respect to radio, but with respect to the overall management of the device to the core network. So this has to be the master, because that's the reason if you see from the hierarchy point of view, the NAS is the top entity, and that's been terminated in the top entity indexing. So the green is the guy, fundamental guy, which talks to each other, and a lot of other things becomes the service to the green layer. Okay. Now, when we do this session management, that's very interesting aspect of it. Now, interesting aspect is like this. Like, for example, this is a protocol entity in the 3GPP. Now, what happens to the device that is above to this world actually? This is nothing but the device's application world. Your clients, YouTube client, everything is being stationed here actually. All my apps and everything. This is the apps world of the device. And this is the protocol world from the 3GPP. Now, how they talk. Now, that is a big entity that we need to be aware of it. That whenever we say a session means that you're trying to do one transaction. Say, for example, we start a YouTube session. Okay, you start a YouTube. But for a 3GPP world, whenever we interpret, we think that is a session number 1. I want to start a voice service. That is my session number 2. I want to do one Times of India web page browsing, session number 3. So like that, I can keep on creating one sessions. And each of the sessions has its own quality of service. Like, for example, a background reading of a newspaper, it's just a background services for me. But a voice is a real time, where my voice rendering software needs every time in 20 milliseconds, one packet actually. So every 20 milliseconds, he's expecting one packet. So it is a very real-time service actually. A streaming of a 4K video is also a guaranteed bitrate service. Now, this is where my service to my 3GPP world get associated with it. with the entity called the QFI actually. So it means that any of your apps knows that he reads the standard and he associate one of his app with one of the 3GPP defined QFI. Okay. So this is the way the apps world tells the 3GPP world that I am starting a service called 4K streaming video. And what is my nearest number for my QFI given by 3GPP? I take the number. And that number will send to the NAS layer. So the now NAS of the device knows that the application layer has started a QFI number 4, QFI number 7. So each of these things 3GPP has defined that the number equal to the services. In the sense like he will say that this is my voice service for take this number, this is my video, take this number, this is my IMS signaling, take this number. This is the thing that for background for URLCC, take this number. So this is where the apps world talk to the 3GPP world based on that. And this is where once the NAS guy knows that this is the number that has been given, one, two services with a number, he wakes up, he knows that what is the quality of service that is meant for this and invoke to the AMF session to the first he has to get an access to it, and then he will see that how the session management takes care of it to ensure that it means that whatever the quality of service demands by the UV, whether the core network will adhere to that quality of service. This is the big things that happens between the device and the core network, because base station doesn't play any role here. Base station is only come to the second role I'll talk about. So suppose a 4K video, the quality of service with respect to the packet rendering, if the core network says that I cannot give you the service, he can downgrade the service to another QFI. He may downgrade, but then the device may not like. It is up to the application layer that has been devised for actually. He may like, he may not dislike. And this is where we call as the quality of service negotiation between the device and the core network. So it goes in back and forth. Sometimes, because not every time we can go in so many back and forth, because it is a cost to the network, because the base station has to come, he has to reserve OFDM resource, all the stuff he has to, because the signaling is going through, and base station doesn't play any role on the NAS packet. So that for this negotiation, if it goes in seconds, then it's very ineffective actually. So somebody has to mellow down. Either the core network says that yeah, this is what I can give it, whether you accept or you can reject. Now the onus is back on the device because he has initiated a service. So that's the way the negotiation happens, and some common agreement happens between the core network and the device application that, okay, I'm ready to go with that. Now, once the core network sees that one, he will tell the base station RRC layer that this is what the quality of service has been negotiated. Please ensure that quality of service in the air interface. And I will ensure the quality of service between the other core network within the routers, between blah, blah, all that entity switches, optical networks. When I talked about the cross-haul connectivity actually. So now you can imagine that the quality of service is just not on the air interface. Packet drop, this, that, wireless fading. It's not like that, because the quality of service is end-to-end, means moment a packet gets generated from the device, in every part of the world has to be aware of that quality of service that has been negotiated between the entities. And that is the role that core network plays a big role. He configures the base station saying that please maintain the quality of service in interface. And he will tell the other entities called UPF, I'll talk about, that please maintain the quality of service that I negotiated with the device, so that holistically the packet goes beyond the core network successfully, because the internet world, the operator doesn't control the internet world. It is ISP's world actually. So for that guy, I cannot control, but I can only tells something to the interface router actually between the operator and the ISP. He can only negotiate with that. Other than that, he doesn't have any role to play. But within a packet, within my network, I ensured the quality of service has been ensured. And to make it happen, we need to understand the protocol. We need to see that how the IP protocol, IP quality of service has to be invoked. A lot of things goes in the background, how the router has to be configured. So the routers, switches has to be configured, and based on the quality of service, a lot of things happens, and then we come back to the router world, because wireless is only a subset of it. The biggest thing is the connecting between these entities in the Ethernet world or the optical world. So I have to configure the optical switches, the DWDM switches with respect to the what lambda, what QoS has to be maintained. I have to configure the router, that what is the marker for their own quality of service protocol to be maintained, the scheduler to be maintained in the routing world. Everything has to be configured with the one configuration entity that the device and the core network has agreed upon with some quality of service. So this is a big entity that happens in the background, and it happened just like a fraction of a second, because I don't have a time waste any point of time. It happened in a rocket speed actually. Moment this negotiation happened, then it's ready to send the packet. I don't expect any single millisecond delay over there actually. So that's the entity that it goes in that order actually. Okay, so to do that one, so I talked about the RRC applicability, and I talked about the non-access stratums applicability. I'll skip this slide and I'll now jump into what we call as the layer 3 algorithms in the RAN space actually, radio access network on G-node space actually. So here, the first thing that happens is that the RRC actually configures what we call two algorithms that runs in parallel, what we call as a radio. Moment see radio worms, remember one thing, it is the OFDM world that we are talking about. So in the OFDM configuration with respect to my pools, resource pool, with respect to a lot of this nitty-gritty, this is the dedicated control channel. The search phase, a lot of things get configured by this RRC actually. And these are all algorithms driven actually, how we efficiently, because this is a control channel. And I told about that downlink control, if it is not configured, then the base station cannot send any data packet towards the device. And if the device is not configured with the uplink control, then I cannot receive any packet, and vice versa, from the device to the base station. Now, what is this configuration? Like, for example, if this is my resource grid, that the RRC is aware of it, and this is my time domain, my symbol level, 1 second symbol, first, second, third, like this, and this is my frequency domain. Now comes what is my efficient resource that I block for my control, like whether I block this radio resource, this radio resource, this radio resource for the PDCCH, because anything you talk about, the control needs the radio resource to transmit. Now, if I block this radio resource, then what is the PDACH resource that is left out? Will it affect the throughput? And this is another big algorithm that starts kicking in actually, because I wish to block a lot of resource, because I wanted to send a lot of control information. So more I block, the less is remaining for the data to go. Now, this is where the push-pull happens in the algorithm, that if I block more, the data throughput goes down. If it goes down, how many users that are there I have to worry about? Is it sufficient, necessary and sufficient? Or I cannot do it, or I have to reduce less. If I less, then if more user comes in the system, then there will be crunch of the signaling radio. These are all my signaling radio resources. Then comes the algorithm starts coming in actually. So this algorithm fixes that what is the signaling and what is the data resources of OFDM has to be been balanced actually. Now, how to be balanced? Any innovation is welcome actually, and it has to done in a dynamic fashion actually. Means at night, say 11 p.m. there is no traffic. Why you want to block where hardly few users are talking? Why you want to block a huge control resources? Okay, you can give it back to the data resources, and vice versa. So this push-pull happens n number of times in the whole 24 hours actually. And how best you actually write these algorithms tells that how best the radio resource management is been there. And these are your differentiators into the system actually. So how you plan your bandwidth configuration, like BWP part actually. That's what I talked in my physical layer. That whether you take your frequency domain and you divide into 4 or 2 or 1, what is the best method? What is your application need? So this is where the radio resource management guy kicks in before the scheduler kicks in actually. Remember, that the RRC who has to be kicks in first actually. So this entity, once the algo finishes his job, it gives back to the 3GPP protocol entity to do some signaling. And then comes the ordinary stuff of doing the signaling and tell and make the mobile aware that this is the configuration that the algo of the base station has done it. The other things that we are brainstorming is what we call as the dynamic spectrum sharing for LTE 5G coexistence. It's very, very hot topic now actually, what we call as a DSS. So how this single OFDM resource, this is my resource, which part you take it for 5G and which part you leave it for 4G actually. What is the mechanism? That itself is a thought-provoking question actually, that what is the mechanism that we need to do this dynamic spectrum sharing, and it's called dynamic, not static spectrum sharing. So a lot of optimization rule happens here. Innovation kicks into the highest level to come back to this radio. And I'll give you a snapshot on day 3, very, very low end. And this is where the innovation starts actually from the product research point of view. A lot of papers you can see IEEE has a lot of papers that for the last, in 5G itself for 4 years, so many paper has been done. But the biggest problems like this, these all things works in a tandem actually. It is not like one goes to the other. One kicks in, one algo kicks in, the next algo takes off. The next algo kicks in, the third algo stops. And they're all working in a very synchronized manner actually. So no paper in the world has done all this algo in a sync mode actually. Because that is not the subject that I understand, but that is where our product research starts to holistically take into account that algo 1 boundary is this one, it stops, then algo 2 kicks in little early, stops here, algo 3 stops like this. So algo 2 has some bit of overlap with algo 1. Algo 3 is a totally different entity, has to start after algo 2 finishes. So this is a bigger entity that we all have to worry about. That is one aspect. Now, after we all do all the stuff, then the data starts flowing. Means YouTube is going, voice is going. Now, before the voice starts, just before the voice starts, the mobile is aware of all the resource configuration, what algo has done it. But what we call as a radio management part is still not complete actually. It means that another algo kicks in called what is called the admission control. So this is the entity runs in the background of RRC to really admit not the genuine guys. They're all genuine because they are all authenticated users. But the users that are intent to use the network at that point of time, that is the admission priority. So suppose a lot of times you may see that you are trying to latch that scenario we used to face earlier. You may be debarred from using the network for certain duration of time because the network is already congested actually. Or I can say that, okay, there are some 10 users are there and one high priority call is coming. So I can actually take this guy and drop one of the user. So my total entity is still 10, but I'm able to take one high priority user into the network because he may be a VIP that has to get admitted at that point of time, or it's an emergency call or whatever. So this is what the admission control algorithm kicks in actually. Then comes the mobility, like when it's our old philosophy of handover, how best you can write your handover algorithm. And here we have experimented with all sort of AI ML algorithms here actually. Easy to work, and a lot of good papers has come out for the last 2 years in the mobility and management aspect of it. Means how best you play with the handover scenario actually. The load management, the quality of service. What is load? Load means that the base station can only support 25 users, and 26th user is coming into the network. So how you manage the load, because your capacity is 25. So either you can drop using the admission control, or you take this guy and take this user, go and purposefully do a network handover to another base station. You can put in another base station that is matches his quality of service. So these type of load management is another big entity that we have to write algorithms. And this where we write algorithms and invoke the protocols to do my job actually. So protocols becomes my service, and algo is the innovation. Moment the algo stops, then the algo calls the protocol to do whatever his job is. Okay, that is what we call the load management. The quality of service I talked about. That now the question that comes that the core network tells the base station that I have negotiated a service with a device and please do it. Now, this is where the base station worries about that whatever the quality of service that the device and the core network has agreed upon, how to do that, how to ensure it, whether I take the help of admission control, whether I take the help of the load management. This is what this big starts actually thinking, that how the quality of service has to be managed actually. And this is where thousands of papers has been done. It is very old philosophy that radio management is happening from 3GPP has really perfected from the 2G days. And these are all not new ones, but what is happening is that every time the standard is moving, some new things are getting added, or we are modifying it actually, because the need of handling the high reliability in the network, low latency in the network. So how to do it if they're already congested and one reliable services needs to be invoked? How to do it actually? Which is the penalized guy you have to do it? How I reduce your throughput one guy? Somehow I tell the scheduler, please control your scheduler as your RB resource towards that, so that I can able to accommodate and free some radio resource for a high priority users to get into. It's a big entity, big thought process goes there in doing that algorithms development. Okay, so these are all my day 3 work, but this is the foothold. You will try to understand that how this space is creates a lot of PhDs, a lot of person worked with us to innovate in this order actually, of making this algorithm to work actually. Okay, now let's come back to the last part of my things with respect to radio access and the core before I enter to the core. Now, the base station. Now, if you go back to my earlier slides here, I talked about there's an NG guy, if you remember here. This is the NG actually. And this is the person where you can see the base station is actually talking to the core network actually. So this is an interface protocol, that 3GPP. Now this ensures that if I don't use this protocol, this vendor cannot talk to this vendor actually. There may be a disparity vendor, but two vendors can talk because they are all talking to the same language called NG protocol actually. And this is where I want to talk about a little bit. I don't want to get into the protocol details of it, but this ensures that the protocol, the NG protocol, talks between the RAN and the core network actually. Because remember that this is a service, like the RRC handovers the packet back to the NG. and NG forms one protocol and he sends to the core network, and vice versa. So it talks about the PDU session. Like PDU is nothing but, you imagine the session that the core network has negotiated with the device. I have to tell to the base station. I have to tell the base station, like, please talk to with respect to the handover. There is a paging that needs to be. Paging means that there is a packet that is waiting for the device to be sent. So I have to tell to the RRC, please wake up. Please send this paging message to the UV. So all these things happens with respect to this, what we call as interface protocol actually, because this is where a base station will know what is this core network wants him to do it, with respect to the early warning, with respect to the tracing of a user, with respect to the UV's capability, paging, handover, all the things is a service that the core network tells the RAN or the base station that this is the command I am giving, and please act on this command and do whatever you want, you are supposed to do actually. Now, then who is the authority of the network? So now coming back, the first thing is that the network authority is not this guy. The network authority is what we call as the core network. So I just skip the slide. I'll come back to it actually. I just to put this, that the network authority, and this is the biggest part of the 3GPP innovation that happens. We all decide that a core network, once we decide the physical layer, the physical layer team does all the waveform part of it. The layer 2, layer 3 teams does the protocol for the radio access. There is a big group in the 3GPP who are worried about that, how this core network entities and what features that we need to worry about. And that is another group that works very critically. And what are these entities are actually? Let's give a little bit of the glimpse to it. I have just marked some greens here. And now you can see that apart from the network entity, if I just add it up, if you just add up the whole aspect of it, I just put one called radio access. One very small entity here. Now you can imagine that a operator world, if he wants to deploy a network, all the things he has to buy it from somebody. He has to buy it. This also he has to buy it, but so many things he has to buy it actually. And this gives a different, where we normally start making a product. So a lot of vendors are there in the world who makes this core network as their products to be rolling it out in and very well known guys are there. So those guys needs a person like you to understand the protocol, understand the 3GP standard, and you have to be thorough enough in the software engineering. And then we have to implement these products in a virtualized manner or non-virtualized manner, actually, whatever. So we require a lot of people like you to come and join this, making this product for the core network. And so many products are, and we try to become master in one or two or some bit of this entities actually, because this itself is a different world like radio access network. And it's a much bigger world actually, because that is what I want to start giving a glimpse to it. Now, the first glimpse I want to tell you, when we have drawn that picture called AMF actually. This AMF is called access. Now, click on this word called access. What is access? This is the guy who actually monitors the user to come to the network. Okay. And this is the guy who also monitors the mobility of it actually, of the user. Okay. And that's a new product that defined called AMF actually. Okay. So the RAN talks with some protocol with them. So this is the person who takes care of your registration process. Okay, it means that whether he can veto you, saying that you are not a right user for my network, and he can throw you out actually. Okay, the person who can lawfully monitor you. He is the person who can make sure your authentication authorization is maintained. Suppose, for example, you're not supposed to use an ISD services, okay, but you started doing an ISD call from your mobile. So AMF guy will come and check your service requirement, whether you are allowed to do an ISD or not. And if not, he'll throw you out. Actually, he'll not allow that ISD to go. Okay. He's the person he's the control of doing your SMS. Means the SMS that goes, you send the SMS in a 5G, he will control it actually. So he's the person who does the location-based service. Means that suppose you stay in Electronic City area and if you want to do some advertisement of some things, then I'll use the AMF guy to use that service, location-based services. This is the biggest entity that for the 5G to make sure that you are registered, you're authenticated into the network. Now, once you're there into the network, then the second guy kicks in called the session management. I talked about the session guy. Remember the NAS guy? There is a NAS guy. So NAS session management module of the NAS is where you demand the SMF accept, or SMS can veto out, or SMS can modify. So this is the person from the UE talks to the SMF who does the quality of service, overall quality. I'll not say quality. This is the quality of the management that comes. And this is a big entity that we worry about, because SMS knows the health of the network. Which base station is choked, which base station is into some scenario of bad coverage. A lot of things he is aware of it. And he is the guy to do the quality of service negotiation and tells that, hey, user, your 4K video request is not honored actually. I want to downgrade to 1 Mbps type of scenario. Are you ready? Then the user may say no. Then he'll say that, okay, bye. So that way the negotiation is closed. Or the user says that, hey, I am okay with that. So there will be a buffering that is okay. I have my application protocol has to take care. So if you are okay, the device says okay, then the SMS will tell the base station saying that I have just negotiated this quality of service with the CV. Please ensure that this QoS is maintained. And then the base station kicks in and kicks his own quality of service management, that I got a request from SMF to maintain the quality of service. Then I need to do 4 or 5 different steps to do it actually. So this is the person is the very important with respect to, so when we get frustrated of not getting the service, that means that SMS is, when we know the debug of the network, we straight away see the SMF to see that what he is trying to see the network. Okay, because once he is the master to tell your quality of service to be adhered, not adhered actually. If adhered, well and good. If not adhered, some problem he's perceiving it. That is the biggest part of this SMS part of it. The another big thing he does is called the IP address actually. Remember, this whole things is IP address based system actually. So I know you, or you are known to the world based on IP address actually, whether IPv4 or IPv6 aspect of it. So, and obviously there is you are under one of the 3GPPs or the operator's own private network actually. So this is the operator world and this is the internet world actually. So now the question is that if I want to use a public IP, so this is where this happens here. But to know you in the system, I use the private IP. So when I want to send a packet in the packet switch network, the whole things happens with respect to that what IP address that has been given to you actually. So more and more users are there, more and more IP allocation pool has to be there. From that, I give you an IP to it. All that stuff is been managed by the stuff. It's not only that If I don't have an IP address been allocated to you, then you cannot get into the network at all, because I don't know, even you are authenticated, whatever. These things will stop it at that point. The third entity is nothing but what we call as the user plane. This is where the base station connects to the UPF, and this is UPF is the last world to talk to the internet actually. And this is where the internet world talks to neither SMF or AMF. It talks to the UPF server, and from where the packet routing, forwarding, everything happens with the policy management. This is another big algorithm that we normally write it here, with respect to the traffic steering, with respect to redirection, buffering, queuing theory, everything that happens in this part of the UPF aspect of it. So whatever our IP world protocols, some bit of we put it in the router world, a snapshot view also get populated in the UPF servers also. And this is where the UPF sends the packet to the radio access, and where the radio access sends the packet back to the device world actually. So this is where, if you see from the hopping point of view, the packet, it doesn't go into multiple stages. It has to cross the wireless world, come back to the base station. Base station sends the packet to the UPF, and UPF forwards the packet back to the internet world actually. So this is a very straight flow, and we are trying to optimize this flow as low as possible because of the end-to-end latency that we are worried about actually. Because more things we put it between the RAN and the UPF, more latency has to occur actually. So this is the simplistic rule in our things, that how quickly the internet world packet will be transferred from device to the end server and vice versa. The last two entities, I'll just quickly go. It's called the policy, and initially we used to call the HLR. Now it is called the Unified Data Management. So policy is where the operator world starts actually, where whatever policy he wants to enforce in the end-to-end network, he defines the rules here. And these rules get percolated to everybody, and through via medium, means this is PCF works very closely with the core network, but whatever the rules, whatever SMS will work is based on this policy, what the operator wants to devise it. Okay. So if he wants to say that, okay, I want to honor few 4K video users in my system, that is a rule. That is a policy he has defined it, and everybody has to honor that policy actually. So SMS will take that policy and do something on that matter actually. Or if the policy says that, okay, if one VIP call comes, the low priority users has to be knocked out. That is also a rule. The rule will be read by the AMF to do this access as part of it actually. So that's the way the rule starts happening, and operator spends a lot of time changing these rules based on the rule at maybe at 10 a.m. the rule is something different. The rule at 3 p.m. the rule is something different. So this is where the operator starts innovating and controls his network actually through the policies he wants to do it. Then the other people executes the policy actually. So the operator thought process is actually written in the PCF world actually, what we call as a policy control function aspect of it. Okay. Not much of innovation here. Innovation that how you think from the rule point of view. That's the innovation of the operator's world actually, because if the operator messes up on that rule, then you can understand everybody is looking towards the PCF. All the rules that will percolate a wrong way. So all the algorithms that are been conceived in one-to-one in every part of the entities will start behaving in a totally tangential way actually. So that's the reason that operator is very, very cautious that I don't send contradictory rules actually, because then one guy will contradict the other, because algorithm can come from disparate vendors, base station vendors. If he has some rule based from the operator, it may contradict what the rule that SMF is trying to do it actually. So that way, a lot of things that we need to take care from the rule point of view actually, that operator's vault has to take care. And the last part is the actual database, like whenever the operator sells a service to you. So that's a database that he mentions from the UDM point of view. So this is the operators world. I didn't got so many things are there, are the part of it, the exposure function, the analytic function, a lot of things that 3GPP has defined it. So it's left to the operator that how they want to take each of these entities. But some of these green ones are very, very important entities just to start the operation of the network. And then you can grow, keep on growing it the way you want to add up more features, more complexity, more flexibility. You can keep on configuring one by one, or you add up new features, new servers based on this capability and all that stuff actually. Okay, so this is the core network part of it. And now you can see the way the operator thinks he wants to deploy a network actually. Okay, now we just cross this part of the RAN actually. And now you can think that operator, we have to deploy the AMF, SMF. The policy he has to define, the policy server he has to define, and some bit of the UDM he has to define. And he can start off, he can roll out the first level actually, and he has to take the UTF-2 account. And the packet can go from the user to the internet world like this actually. So the way he thinks that, okay, let me have one level of deployment with respect to the roaming. Because remember, all this architecture, we don't feel, we normally cross the geography, states, boundaries, countries, but we still able to talk to each other. So what the standard tells you that the two architecture you need to work about, what we call as a roaming architecture. And one is called the architecture with which you want to talk to the visiting location actually. Now, just imagine that we are here, a user with his home location, he's doing some service and he's crossing the boundary where he's going it to some state or some country, and he's land up into this part of it. Obviously, there is a roaming agreement between the operator. When you say that operator 1 and operator 2 in some part of it, there is an agreement that happens that to accept any of your people into the network actually, into my network, and vice versa actually. So that's the agreement. So we normally try to think of that when two entities talk actually. So there is an entity that talks with respect to the roaming, because the two core networks, one aspect has to talk each other, to authenticate, to do everything based on the fact that I have a roaming agreement actually. So with which we define the roaming architecture actually. This architecture is based on that you have an agreement between these two operators, and these two network function entities. You can see that only some aspect get talked, not all the entities talk into the architecture actually, not all the things participate. Only the SCP part of it, the visiting and the home guy, they talk to each other to ensure that the right person has moved to your network. They get authenticated, and then only they say that please go ahead. It is my own subscriber. It is not a ROG subscriber that has opened got into network. And then this guy accepts and signals saying that please do the admission control and all that stuff. Please accept him into the network itself. So now he's roamed actually. So that is where we need to think of that in a operator, when he works in a standalone mode, I can still do it actually. So I don't need any roaming agreement. But if I want to get into the roaming agreement, I have to have this entity functionality in place to do my roaming architecture as part of it. But actually 3GPP didn't stop here actually. What he did also, and it started from 4G days actually, and he's very collaborative in nature. And he thought that why we want to accept only the user with a SIM actually. Why can't a non-3GPP access guys can also use my network? And the biggest example that we actually did it is the Wi-Fi actually. Because if you see the Wi-Fi domain, Wi-Fi also has this access point and his network authentication everything mechanism, mobile IP, everything is there. But if he wants to come back to the 3GPP world, actually, so he can use the services of the 3GPP entities, actually. So he can use the access mechanism. It means that I can also authenticate given access and controls the 3GP Wi-Fi's access points, actually. So access point can actually now has the ability to talk to the 3GPP's access core network, actually. And that is not in 5G, actually, it started in the 4G. So rather than you have your own authentication, own AAA, own HLR mechanism, you can use my network, my core network fully. So you have to just have an access point, whatever the Wi-Fi routers that you are having it. And if you have the capability to talk with the interworking function that is defined by the 3GPP, if you have that software in place, then I can give you the ability to introduce that a Wi-Fi guy can be authenticated, monitor, authorized, everything by the core network itself. So this is where the biggest things that we are pursuing it, that what we call as a Wi-Fi to say 3GPP radio access handovers, actually. Say, for example, in some geographical area, one use case is that you have a Wi-Fi network, actually. And your EV has both Wi-Fi radio and you have the, say, 5G radio connectivity. So we can do this handover very easily between each other with this mechanism itself. So this is the biggest asset that 3GPP is trying to make sure that the Wi-Fi guys can use the core network for handovers, for authentication, authorization, everything. So a little bit of the details. I'll not get into I just wanted to give you the glimpse of the complexity that how a core network protocol is been envisaged and has been thought of with respect to the interface I talked about, with respect to the NAS protocols. If you think of the NAS, talking with respect to SMS, policy, location services, and talking to the core network, and it's just, you can see that EV is talking to the SMS, AMF, all this world, actually. So this is the complexity that the core network is giving back to you. And this is where the protocol peer-to-peer reside. If you see the arrows, the peer-to-peer resides each other, actually. And there is an entity that talks about with respect to the user talking to the access mechanism, the user talking with respect to the session mechanism. It's pretty complex with respect to control, that we set up a context where we accept that the mobile gives the quality of service and then roll out the algorithms, actually. So in the backend, every such entities get invoked when we do the transactions end to end, actually. Okay. In the similar lines, we do this, what we call as the user plane in the core network, where you can think of the access network is nothing but your base station or the G node B. And here we use a different layer 1. This is not the layer 1 you think of the air interface, but this layer 1, layer 2 part of it, there is the IP world that starts talking about with respect to transferring. Here we can use a typical TCP/IP UDP, and here you can see that we have taken the ITF UDP protocol to do the transaction of the user plane packet from the base station to the UPF to the internet world, actually. So that's the way the things goes in a end-to-end aspect of it. And vis-a-vis, I'm just putting forward what we call as the untrusted network or the Wi-Fi network. So they also can use the 3GPP interworking function to send the packet towards the core network. He can take the interworking function to the UAPF, and rather than terminating to the network through the packet data network of the Wi-Fi of your DSL, we can still go ahead and use the UPF to terminate the Wi-Fi packet towards the internet world, actually. So this flexibility here is given, actually. It means that 3GPP is not only taking into account the mechanism to accept the 3GPP's own devices, but it also is accommodated to take the non-3GPP like the Wi-Fi guys to take into account of the packets that's going into the internet actually world. The other part is one thing that also comes is that what we call as a tunneling protocol. I don't want to get into that detail, but the tunneling protocol is one of the important piping mechanism that defines that how the core network understands the packet coming from this EV1. So EV1 goes through one tunnel 1, EV2 will go through another called tunnel 2. So this is an identifier. And with this identifier in the day 3, I'll show you that how we write the quality of service to be invoked and maintained and enforced, what we call as enforcement part of it. The enforcement happens in the UPF world actually, and that is helped to this identifier called the GTPU tunnel. And we do this lot of this enforcement to identifying you that how is your packet flow, what is your packet arrival, the rate that I'm seeing it, where is your congestion, how I improve, when I want to do a buffering to your downlink packet. A lot of things that we normally do in the quality of service enforcement point actually in the UPF. That I'll reserve in the day 3 protocol when we talk about in that aspect of it. So this is the glimpse that you can now imagine that the core network, when we say a core network point of view, it is pretty complex in nature actually. So it is mainly governed by the architecture that is fully given by 3GPP. The algorithms are less, but there are a lot of important protocol messages and a lot of innovations that we do with respect to the controlling the admission control, with respect to the quality of service, SMF, policing aspect of it. That is the what we call as the operators innovation world actually. See, one world is where the researcher like us, we innovate in the radio access domain. But the operator, when he thinks that I want to play with my network, okay, let me do very a time-based quality of service, whether I want to do this, I want to do that. So the operator does his research with his network. He wants to ensure that the overall network quality, handover, call drops are maintained, how to maintain it, what policy I want to change it. So this is where the operator comes in that world, where he closely watch with the rule-based system. He talks to the vendor saying that this rule is not enforced. Hey, look into that. A lot of things that comes in the operator worlds. He works very closely with the core network vendors to realize his vision of the network. So when we say a network, in the hierarchy point of view, the core network is at the top of the entity, and down below, if you just see this part of it, this is where the domain where has to be laid down first, the vision of the network, and then only we can work in RAN, we work in here. So this is what we call the vision of the network starts, that how I design my core network to talk to say thousands and lakhs of base station. Millions of 400 million subscribers have to talk. I have to talk with say 300,000 of my base stations. So now you can imagine that the magnitude of this planning, 400 million subscribers, the database he has to work about to handle in that order, the policy he wants to enforce that takes care of both from the session, the radio access, the base station, and the device has to work seamlessly. He's been controlled from his vision of the rules he wants to put it. What analytics, how he wants to slice the network, how he wants to put the analytics into the system. This is what the vision of the network operator starts actually. So the first thing he's worried about that, hey, whether the 3GPP standard has been laid out based on my vision of catering to a EMAB service, or whether URLCC service, or with a massive IoT service, is based on the vision that he tells the operator to the 3GPP body that this is my 5G vision. Please ensure that the entities have been taken care of it. And that's the reason when the 5G got rolled out, a lot of this micro details was being refocused actually, because my service layer is changed actually. And this is the first part I want to tell you, that it is not from the bottom-up approach the standard works. It works from the top-down approach, where the vision of the services, the core network, then comes the radio access, mobiles, and all that other stuff. Okay, so this is the first part. I want to close it off at this point. The next part, I want to just quickly go back to a few slides here, where we talk about what we call as the procedural aspect of it. Now you know the gamut. The gamut, we are all clear now. So it means that the core network will be there. The core network will be talking to the multiple radio access network, 1, 2, up to n number of radio access network. Each radio access or the base station will have m number of UEs, actually. M users are there. So this is the overall aspect of it. So n base station, m UEs per base station, 1 to L core network entity system. Now imagine we have laid down, the network has been rolled out. Now one such users like us has powered on the mobile phone actually. And once he powered on the mobile phone, how he get access to the system actually. Like I talked about that there is an authentication, registration, that is the NAS guy will come. All the stuff has to happen. RRC has to come. But if my physical layer is not first to detect, then nothing happens actually. Now let's see what happens here now. Suppose I am a device. I just switch on my phone. Now, moment I switch on my phone, though the software comes up, but I told you there is a NAS who's the authority and he controls the physical layer of the device to say that please start the cell search procedure. Okay. So this is the master actually. When the switch on the system, the role of the NAS comes, because if you see in the hierarchy of the stack, the NAS is the first guy, then the RRC, then the PDCP, RLC, MAC actually, that's the way. And the layer 1. But the master now has wakes up. Now he has to know, he has no clue that which network he is talking about, whether he is in the home or whether he is in a visitor. He doesn't know any clue actually. So to come out from that clue, this guy says that, okay, NAS takes a control and his mobility management entity module of this NAS now will tell its own layer 1 of the device, please keep a cell search. And this is the first algo that is not defined by HTTP. So 3GPP does not define how you want to do the cell search. And this is a lot of innovation goes from 2G vault to the 5G vault, that how you actually scan and then decide that this is the network to it. Now, network to it is much later aspect of it, but to come to one specific frequency, that itself is a big job actually. Why? Because I in the first day have shown you that what 3GPP has defined, what we call as the band of operation. So the whole gamut from 700 megahertz to say up to sub 6 gigahertz, there are a lot of these bands that has been defined. And each geography has taken some band for their things to start their operation. Now, suppose a geography has, your phone is a roaming phone that can take up to multiple bands. So it can support this band, this band, this band. Now within this band, there is a minimum and the maximum frequency. Now each of these things is one frequency F. And there are so many Fs can be defined here across the bands that he's supporting it. Now where to start? Now the first question is from where to start. That itself is a patent, that from where to start. So a lot of this operation or papers, patents that we can see that how you start making sure that you start your scanning actually. This is what we call as a scanning. So whether you do a sequential scanning, like you start taking the first frequency F1, you take say frequency F1, add say 10 megahertz, go to the next frequency F2, add another 10 megahertz. Like that you move in that order, or you have combination of going to 20, or you go to the next based on 100. Now, what is the mechanism? Whether I change this whole band and move to the next, say, 26 gigahertz band, how to do it? So that itself, the start itself is the patent and papers we research. And the device vendors are very cognizant to start that how best the cell search, because if you do in a sequential and do in that order, it may go in hours to complete that whole band search itself. So how quick? What is the mechanism that we have to decide upon? Now, suppose we decide upon the start, and suppose you are able to match your frequency with respect to the operator defined frequency. That is that you are able to find a match to that frequency somehow after doing the scanning. Iterative search or sequential search or some sorting search, whatever mechanism you can think of. Somehow I am able to get his frequency latched on. The first thing I have to do, I talked in the morning, in the last day one, is that there are two sync signal that the base station is keep on sending it like this. The primary and the secondary synchronization signal is been constantly been aired into this slot actually. Okay. Now suppose the sunny day scenario, I woke up my phone here. But the question is that there is no PSS here, they're all white. But what happens that I'm able to get my frequency latch, but not able to find the sync pattern. Now, how you do the syncing? I'll leave it to the method that I'll talk in the day 3. That how we do the correlation here actually. So when the mobile woke up, he didn't find any correlated peak here. So then what he will do? So whether he'll drop his frequency and move, or he take a chance to shift and see that, okay, he may find some samples, maybe at some point of time, because this is the time actually, by the way, this is in the time axis. So another algorithm that whether I drop or I may found it, but I am not able to find the PSSS signal. So maybe it's not right, or it may be an rock transmission and all that happening. So then he may, if he decide to wait, he may again come back here. And this is the first part he can think of. That is the first, this part. He may be able to find it. Now the luckiest part, you have seen it here, is that they're all closely spaced, what we call as a SSP transmission mechanism. But if they are sparse in nature, like one comes here and another comes at here, then the mobile is in a perplex mode that the base station has configured that he doesn't know, by the way. So he keeps on doing the iterative search here and take the samples, do the correlation, take the sample, do the correlation, and suddenly he may able to find out, hey, my PSS local signal, local PSS, and is matching with my received PSS. So there might be that I'm very close now. So I able to get him. But if he's if the operator has set up a very sparse location of this signal, then you can imagine that mobile is perplexed and keep on doing his job. At a time, he may decide that let me abandon this frequency and go move to the next frequency. He may take that decision also. But what happens to the base station that if you keep on changing in this order, if so closely spaced. Now remember that same block I talked about, the radio resource guy. When we run this algorithm, if I do this one very good, that mobile able to latch on. But what penalty I'm playing at? What is the penalty I'm taking care of it? Now just I'm doing the grid once more. So this is my grid. Now in this grid, I have taken the slot for 4 symbols and few RBs for my PSSSL. This one is going in here. The moment I take this one, the remaining part is my data throughput actually. So it means that I am sacrificing my data throughput. How much? This is very fundamental question. That is where if the algo is wrongly written, then you can see the penalty I'm been given. Now another penalty. Suppose if I sense in this closely spaced blocks actually, it's very good from the mobile because mobile able to just skip few symbols and few slots and able to latch on the network very quickly. But now imagine that if I keep on doing in this fashion, so every such slot duration, I'm sacrificing my throughput penalty. Okay, that is not good for the network because not if all the users are into the network, this is an overhead because all the guys are registered into my system. And if I still send in this orders, closely spaced order, then my throughput for these users are being sacrificed miserably. So what is the optimization rule that starts? So this is the big things that we normally work upon actually. And this happens in much in the planning stage itself before we get into the cell search, because cell search by the time the radio resource management algorithm is already running in background. So if it is cell search is taking longer time, then we do this dynamic reconfiguration to say it that, hey, my planning was wrong, my algo is not firing. Okay, so this is where the cell search mechanisms not only tells me that how quickly I able to make the user into the network, but it also gives me the feedback that the average cell search time may be 2 seconds. So for 2 seconds, the mobile is waiting, and if it is an emergency call, or if it is a high low latency call or low latency session, this 2 seconds itself I cannot able to tolerate actually. So now the push-pull starts in the network. That is this optimized? And that is where we spend our brain to do that mathematical optimization that is suitable for writing a C code optimization. That is the implementation aspect of it. But the algorithm has to be optimized in such a way to take care of low latency, cell search time. And this is where moment he does the cell search, then the mobile knows that where is my 10 millisecond radio frame boundary and where is my slot boundary actually. So this is the two things, the cell search from the mobile point of view. He is able to categorize my 10 millisecond boundary in the time, because remember it's a time scale. That whole stuff in the OFDM, it works in a time domain manner actually. So I have to make him aware of it, that there is a radio frame that is of 10 millisecond duration that has a start and there is an end. There is a start and there is an end of the next. So that the mobile has to be fully aware of it, and he has to be fully aware of with respect to the secondary synchronization signal that this is my slot boundary. Moment he get in the slot, then he is tuned with the scheduler of the MAC actually, and that is what the intention is actually. Because if you are only with respect to the radio frame, but the MAC works with a slot level, so the finally mobile has to find a slot, that he has to know the what we call as a slot boundary actually. So if these two boundaries are not found, the mobile is not done his cell search. Now, not finding has many implications. Whether my this is little longer, or the correlation is not happening, or the rock transmission of the frequency has happened. A lot of things can happen into the practical scenario. And this is where the innovation kicks in. Just a simple cell search part of it. There are 3-4 entities in the backdrop. For doing just a monitor cell search, it is nothing from the device point of view. There is a big patent that goes in doing cell search, but how the cell search can be augmented in the optimized manner, there is a base station algorithms kicks in doing that. And he tried to see that, okay, this is taking longer time, registration is taking longer time. All the stuff, his optimization rules that he thinks that, okay, I have gave up that the algorithm is not able to do it. Let me go back and tell the operator, please change your policy. Okay, that is where the operator's policy again will start. The operator might think that, okay, I have done a wrong policy, with which the implication is that cell search is been getting affected. Okay, so this is the first part of the procedure one that is very, very important, that the mobile is able to recognize our networks with respect to the synchronization. Now he's synchronized. Okay. Now the biggest thing that I told you that RRC works is that if you see that once he is able to synchronize this part, this is the orange one, where the RRC part starts sending the broadcast. He keep on broadcasting it. So the broadcast is actually augmented by this PSS SSS actually. So this is the broadcast configuration goes. And this is what we call as a SSB transmission from the base station itself, from the G node B. Now, what we tell to the broadcast is a lot of things to the network, to first level, the mobile, and we don't send one shot everything, because remember one golden rule. If you send more bits, this in the frequency event will start growing like this. So the golden rule is that please wait. You take a chance and send so that the load on the scheduler is less. Okay. And this RB, rather than giving to everything to the signaling, so if I give all my radio a resource block, nothing but my OFDM grid, so more bits, so that leads to the more RB actually. And this is where the SCH, the scheduler, is very, very worried about. So we try to cap it out, and standard is able to cap it out, that we send some part by part actually. Okay, so we tell him that, okay, if you're able to get to the network is having the common signaling, that is for the common for all the UEs with respect to some sub-carrier spacing actually. Okay, and the network is not barred. Okay, so this is a very, from the 2G time I'm seeing it that is coming, and this is called the master information block. What is the basic things that are required for the mobile to actually. Okay, and we don't bombard with them, because I told you golden rule, more bits, more RB. So this whole stuff, if you're able to send it out, it takes few RBs, and that we can accommodate. So what we did is that the MIB structure from the 3G to 4G to 5G has been optimized, and optimized with respect to the bits, and the bit has optimized led to the scheduler, so that he able to give the relevant RBs, so that he can place the other RBs to it actually. So this is what we call as a master block actually. And this master blocks also tell him that please read the SIB, the system information block, that is part of my dedicated common, and you'll get some more information into it. Okay, and the cell is not barred. So if it is barred, then mobile will not able to go to the next level of decoding that one. Okay, so that's a way we have condensed the size of the master block, and that is what the things that UE is required to know the some base information of the network actually, of the network. And once he is able to successfully read this MIB block, and in the algorithm we'll see that how we able to do the channel estimation, how we do the equalization in the device side, and that is very pretty common. And we're able to extract the bits, the symbol, we're able to extract the bits, give it back to the RRC of the UE. And now RRC is self-sufficient to know that what is all this configuration is all about actually. And that is what we say, that the mobile is able to successfully read the master information block. But here to read that, because this is a layer 3, but we have to cross the bits, symbols, bits, and all the stuff from RF back to the layer 3 to actually come back and talk about saying that, okay, the UE's RRC now declares that I able to read the MIB successfully. And this is the part that mobile is waiting for. And the moment he waits at that point, he's not stopping actually, by the way, because he starts the next important aspect of it. Why? Because now he knows from the downlink, the configurations. The PBCH configures the UE. Now he starts the biggest operation of the world that is there from the 2G domain till 5G. Nothing changed except something, except the preambles part of it, is that the random access mechanism. So whether mobile likes or dislike, he will start this procedure. Why? Because he has to complete what is called the registration in the network. But before doing the registration, this is a non-access stratum work, but he has to ensure that he tells the base station saying that I want to access the network now. Means he sends from the uplink. Now you can see the device and the base station sends the RACH preamble, and these preambles are what we call as a Kazakh sequence. One of these preambles will be taken up randomly at a random point of time. Doesn't matter, it doesn't tell the standard, and that tells that there are certain slots reserved for your RACH. So this is the RACH slot, this is no slot, this is RACH. Mobile can decide that I will send not the RACH here, but I'll send the RACH here. Who decides? The mobile's algorithm decides when to send the RACH, what point of time. Though the standard says that this is a RACH, he may skip the RACH occasion. The UE can skip it here and can decide here. And he picks up one of the out of the set of the preambles. He'll take one of the preamble here and send it to the network. Very easy to write the random access response. But in the day 3, we'll deep dive here that how the base station actually decodes this RACH preamble. And I'll just put it, the inquisitiveness here, that how our old textbook related matched filter concept, simple rules that we have learned our signal processing, a domain, we'll see that how we apply here, how we do the correlation, apply the simple rule of the correlation. And the base station decides that, remember, base station doesn't know which preamble that the mobile has sent it. Now that's the algo, biggest algo starts in the base station, that decoding RACH actually. So in the day 3, we'll deep dive on that, saying that how the base station decodes a RACH preamble actually. What mathematics that we used from our signal processing textbook that we learned so many days, and how intelligently we work on that. But some more things we do it. It's not like just one correlation is enough to pinpoint here. We'll talk about a little bit of that details here. And this is the algo that 3GPP doesn't tell actually, decoding RACH. And this is the innovations left to the innovation, that how to do it, how intelligently able to do it. And the biggest thing that happens that if the mobile sends a preamble ID 1, I need to decipher preamble ID 1. I cannot tell it's a 2. It's wrong. But sitting at mobile, I don't have any clue, sitting at the base station, I don't have any clue that what mobile has sent it actually. Okay. So as a procedure, we do a lot of things. If you see what we call as a contention based, So contention means that I need to understand that you are you. Okay. So what happens is that the random access send, the MAC comes here actually, that I told you last time. The MAC comes handy here. He sends the RACH response. We get the another message from the mobile, and then we resolve this contention actually. So at this point of time, the base station really knows that he is a genuine user actually who wants to access the reach at this point of time. Before that, it can be anywhere. A ROG mobile also can able to jam a base station actually. Okay. So this is the biggest part of it, that the algorithm able to decipher the preamble, and there is a contention happens, the resolution has to happen. And with this contention resolution, both the handshake has happened between the device and the base station messages to ensure that you are really the right user to access. And then onwards, we are not stopping. It's all goes on beyond that point. So the RACH mechanism is fundamentally the first part of it. Here again, the protocol starts with respect to random access response, with respect to scheduled transmission, contention. These are all governed by the standard. What is not governed by the standard is how you decipher. So if my deciphering algorithm is wrong, then you can imagine that if the mobile has sent 1 and I have sent 2, so if I try to do a contention resolution with 2, the mobile will know that, okay, I didn't talk to the network, and he'll again send RACH. So it means that if this is a wrong detection has happened into my network because of bad algorithm. Okay. Now this can be more words we can put it. If this mobile is moving at say 500 km/h speed, it can go in any direction, this number. So how to come out from that? Because base station doesn't know the user has sent a RACH at 500 km speed or 300 km/h kmph speed. And this algorithm can break at this point also. So a lot of this innovation goes in the RACH itself, and papers is very, very legacy. And so many times we are trying to figure it out that what is the best algorithm that can suit from the propagation characteristic of the physical. So fundamental in nature, this RACH aspect of it. And still from 2G till 5G, this research is a constant research, just like handover. We kept on innovating that how best in RACH. Same thing in handover, how best we can do actually. The another big thing as a feature. So now imagine that mobile has successfully done the RACH. He has come to the network successfully. He has registered successfully, means authentication is done. And now the packet transfer has happened. Scheduler has started taking over in doing the packet transfer, scheduling the logic aspect of it. And then comes the fact that the MAC entity is now been told that please start handling the hybrid ARQ. And this is where the scheduler kicks in to figure it out that how fast retransmission scheme that can be taken care of it with less delay at any point. Because remember, anytime you start doing the retransmission, it is adding more retransmission, what we call as a more retransmission. The delay is more actually. Getting the same packet. Suppose this is the packet that you want to transmit out, and more retransmission that happens. So more delay happens successfully to get it. And it may happen that some point of time, the hybrid ARQ fails and then ARQ starts. That also can fail. All these failure scenarios we need to handle it. So what is this hybrid ARQ? So the MAC only, the scheduler in the MAC triggers the retransmission. This is not the person who does the combining actually aspect of it. Okay. It triggers the mechanism to start the retransmission. But what we call as a combining of the bits, is done in earlier using two methods called chase combine and one called the incremental redundancy. So this is the what method we have chosen now with respect to the incremental redundancy aspect of it. So after a lot of research, we've chosen and a lot of papers that you can read the IR journal paper that how the incremental redundancy works actually. And this is where the problem starts, that moment we send one packet and if the packet is not acknowledged, then we have to retransmit, and some point of time we may say that, okay, the packet has been successfully transferred and retransmitted by through an IR mechanism itself, and it is ready to go to the upper layer actually. Means to the MAC and MAC to the RLC actually. Okay, so till the retransmission is complete actually. Now you can see that the flow, this is successfully done, it has moved up, but this packet has an error in the CRC that has led to the fact that retransmission mechanism, and somehow it has successfully retransmitted here, and then only it went. By the time what has happened now, the third guy has went up, fourth has gone, now the two is coming after fifth, if you see the sequencing of the packet. Now this sequence of the packet, because packet was sent from the base station or either side in the 1, 2, 3, 4. So what RLC goes, what get is that 1, 3, 4. Now you remember I was saying of the reordering. So we have to reorder this stuff once more actually, just to tell that, okay, after 1, 2 comes, after 2, 3 comes. So this is what that protocol will take care of, the reordering. This is the greatest part of the aspect of what we call the hybrid ARQ actually. So that has some bit of the MAC who triggers it, and most of the things that happens in the layer 1 who does the combining actually. Okay, taking the previous packet, new packet, and all this stuff. Now another features that we are very concerned about is called the power control actually. And this is another big feature. And what is a power control means that the device is here and the base station is here. And the base station can send 40 watt of transmission per port actually. But what is the transmit power of the device as per the spec? Up to 23 dBm with a certain category of mobiles. Now, if I transmit at 23 dBm, if my path loss is high, and suppose you also have a high multipath, this power is not sufficient enough to do some transmission, but this is the limit. After that also, if I'm not able to do it, then I have to trigger some other method called handover. Like I want to take this guy out from the network because he has gone beyond the edge of the cell actually. Okay, but what happens, say a scenario like this, he's here in this boundary and the mobile is here. Now, if he sends 23 dB of power, then the base station receiver will start saturating it. And this may lead to a block error, bit error, and it may lead to a block error, a throughput loss. Just the fact that I am not able to control the transmit power of the mobile. That is the reason what we call as a near and far effect actually. So we constantly monitor based on, in the uplink especially, that what is the power of the uplink shared channel because if you think of this as a grid, and this part of the grid was given for the mobile to transmit his resources, say YouTube video. And if you transmit with a full blast of 23 dBm, then the receiver in the base station will saturate. And a lot of things, this is one part of the problem. This guy can create inter-cell interference because he's transmitting at such a high power. Some other base station can also able to see that power actually. So this creates the intercell. So this guy can come from this one. So the important part is that when he's coming near to the base station, I need an algo to control his power actually. And what the standard has helped me is that he has given some equation, but he has left one innovation left out here that is governed by the algo. This is the final detail of it. Why finer detail? Because remember, in our typical wireless communication, we have two aspects of it. One is called the large scale fading, and one is the small scale fading actually. So large scale fading is based on your path loss part of it. But the small scale fading can still alter your signal power with some amount of fade that can also be seen it. Now to control the small scale fading, I need one algo to do the final adjustment of this transmit power so that I don't enter in the blur, I don't enter into the saturation. My throughput is maintained actually as per back to my modulation that the scheduler has given actually. Okay, so this is so important that if you see that power control algorithm and that it maintains with respect to the shared channel, with respect to the sounding of the channel that the base station measured, with respect to the control feedback that the mobile uses to send something feedback back to the base station, or with respect to the PRAC. Everything has to be controlled with respect to the power control actually. If this is not happening yet, there is a disaster result will happen. And that's the reason from way back from the 2G till 5G, we kept on taking these features and we have improved these features day by day. This is, and through these different varieties of algo, that some snapshot I'll give it in the day 3, that what we call as the power controlling of the transmission. Okay, now this may be the last part of it, because now I'm just trying to see the gravity of the algorithm, and I talked about the beam forming aspect of it, and I talked about in last time that when we have an analog beam forming and we have the digital beam forming and we have this hybrid, this is coming from. So what happens to this beam forming is that there are two paths that the standard has given actually. So standard says that I have a beam forming weights that is defined what we call as a code book actually. So standard people has researched and came up with one code book. But standard says that you also can use a non-code book actually. That is up to the innovation actually. Non-code book and left to the algo. So this gives me more flexibility in actually controlling my beam actually. Now what is beam? I talked about that if you have antenna, you do the transmission. But this is the pure from the RF point of view. If I want to control this RF through my changing my polarization and weights of the elements, I can still statically do this with a phase shifter connected to each of this path actually. So this is well-known entity from the old days of radar. So this is, so what we have plugged out in 5G is some subset of it under the purview of the whole 5G network of doing this part of it. So 350 doesn't tell how to decide this analog beam weight here. That's what I've written here. So we generate all the symbols, what the physical layer point of view. And when we come to the time domain, this is where the time domain has happened. And then it passes through the universal beam width before we put it to the antenna elements. So this is what we call as a pure analog part of it. So innovation comes at anywhere that I talked about, where we want to do a cell splitting is one of the use case, where we want to split a large cell. You have a one antenna, large scale, you can make it as a small sectored thing using the analog beam forming actually. It is very well known, it is works, and in a millimeter wave, we do it in a very innovative way actually. But now question is that if it is it static, dynamic, controlled, all the stuff, the sweeping, again, one guy is there in the tier 2 called the scheduler. Now we have put it back to the scheduler to control, to do a little bit of the dynamic. We can make it static also, but we can make it as dynamic as possible. That is one way of thinking of doing this analog beamforming actually. Now, there is another thing that we talk about called the pure baseband actually. Now here, the point is that I was talking about either you can go with the 3GPP way. So you can take the 3GPP code book and you can create a digital beamforming weight you can call, and sometimes loosely we call it as a term called the pre-coders actually. So this is very things that is one way to do it, or this is what we call as a non-code book based, and that gives another dimension of our innovation to do in the digital beam weight actually. So a lot of research goes on in coming up in this. What is the actual digital? Measure the channel, sound the channel, we measure it. Those things we'll talk about more in the day 3. That how we decide the digital beam weights based on the algorithms. Very loose way, because I cannot talk to the innovations what we did. But a very textbook approach I will talk about in the day 3, and we require a lot of people to innovate in the non-code book based approach actually. The third is the combination, is the hybrid. So that we are using the millimeter where we use both digital and analog. And now you can imagine the complexity of the millimeter wave transmission. And so we require how we play around this to both digital and both analog to do a proper transmission, because the fading characteristic of millimeter is totally different. Okay. So taking into account, we thought this is the best approach, and we see a gain into that actually. So this is the things I'll talk about in the day 3, that how we devise the millimeter waves, hybrid beamforming and all this stuff. So, but this is the biggest feature that in the 5G, though it started its innovation in the late 4G spec actually, but 5G has taken up in a big way actually. They have enhanced it, and keep on enhancing this now also, because they are enhancing with respect to the code book that they want to granularize as much as possible. But we are also in parallel, they have given an option to use a non-code book. And so we are innovating in a separate world from the non-code book point of view. So this is what we talk about in the day 3 aspect of it. And my last part will be a little bit of the handover. Again, we all know that from the 2G to the 3G to the 5G, handover mechanisms is where we actually, the base station moves from one cell to another. We have learned this in our wireless communication subject in more details. But what 5G did is that they are able to what we call as the events based approach. This is the simplistic approach, what we call as a mobile assisted handover. MAHO we'll call actually. So MAHO means that I will tell mobile, please send me this events actually, A1 event, A2 event. And the standard defines this event definition. Means standard tells that if the event A1 comes, if the serving base station is based on the threshold. Now just see this word called threshold. Okay. Now this is where the operator controls this threshold value. Now if he has wrongly configured this threshold, then you can imagine we'll be flooded with a lot of these events. And that can cause to the software problem, handling problem. If this threshold is high, then I will do a late handover. So just a threshold optimization is a big subject in our radio management algorithm, that if my threshold is high, I do a late handover. If the threshold is low, I do an early handover. Just this threshold or wrong setting of threshold. Now, what is my optimization rule? In the G-Node V or in the RAN, if this algo is wrong, now you can imagine that either we land up in this scenario or this scenario. Now, this scenario is so dangerous that you will lead to a call drop actually. Now, why this is also dangerous early handover? Because unnecessarily we are loading the other cell where we could have waited also, like the target cell in which we want him to go handover. He's not able to accept you. So it means that I'm doing an early handover, and that guy, that target handovers base station can get choked actually because of early handover happened from some other base station actually. So this is what we call as an event-based handover, and that is what we call as a MAHO actually. And it's all based on this threshold, all the stuff. Okay. So this threshold optimization is very, very important that we have to take care. And based on this threshold, we devise the handover algorithm actually. And that happens in the RAN. And moment what we think is the right time for him to hand over, we give the handover command back from the base station or the RAN to the EV actually. Then the EV moves to the target base station, the RAN 2. RAN 2 is his target base station actually. So first is that if I go with a MAHO based approach, then I need this event to come actually. It's an event based approach. Now to have this event, it's a directly proportional to what threshold I have set. This is so dangerous that if the thresholds are wrong. Okay. So this is what I'll cover in the day 3 again, that how we set up this, the MAHO based approach. Now we have this network assisted handover. So in this network assisted handover, we do this load management and all the stuff just to reduce the load of it. So we purposefully take out the one mobile and tell him that please go out from this base station and to the another base station. Okay, because I have the report of this base station that you have sent it to me. So all these reports are there. So I told him that please go out and go to this and mobile will follow. So it is not what mobile intend to do, because I have find that the current base station is highly loaded, and due to which network assisted handover has been triggered. And that is where the handover algorithm in the RAN kicks in to do that job actually. So now you can imagine that it is not only a mixture of the protocol procedures and all the stuff, it is a very synchronized, holistic manner. The whole things works seamlessly actually. Like it looks so easy, but if you see that the network rolling it out from the standard, when we write a standard, so if you say that, okay, standard has taken this time to write it, another big time goes in doing our research in coming up with all this algo actually. So another big time goes here actually to come up to actually perfect before we deploy it, give it back these products to the operator, where operator is happy to work with our products actually. So it is a big mechanism that goes on from the standard to the product, that, and these algorithms are so complex in nature that a wrong design, a wrong thoughtful actually will lead to a havoc in the network, you can imagine actually. Okay. So this is what I'll stop at this point of time. This one I'll keep it in the day 2, where I'll get into more on the call flow part of it. So anything I want to just tell, I'd come back to the summary part of it. So what I have done in that point of time, I purposefully taken out the call flow number 1, and I'll take it to the day 2 actually, day 3, because to get into the day 3 call flow, I require some of this concept from the core network. Some bits still are left out, with which this call flow will be little bit of, you can able to appreciate that how the synchronous mechanism that happened. So I talked about today the layer 2 protocols, stacks, the algorithms, the L3 algorithms, part of it. RRC, I just given a snapshot view, part of it, that what is the utility of these things in the network, and what are the different layer 3 algorithms that we control. The biggest things I talk about, the scheduler and the radio resource management. This is what we call as a radio management. And I have told you that from the core network, this is actually the operators, the whole network brain is here from the operator point of view. So from this brain, we start doing the top-down approach for making the network. I've given a glimpse of AMF, SMF, UPF. I talked about roaming and non-roaming scenario. And I showed you that how the core network protocol stack of user and data plane looks like as given by the 3GPP. And it's very complex in nature, because you can now imagine that I have written some part of the green entity there. I never ventured out some of the purposefully left out non-green ones in one of the network function slide, because it takes days and days to understand it. It's not the right forum for that. But the complex nature of this is very much, and that works with the operator's policy control function, where the operators actually innovates using this one and see that how the network performs actually. Okay. And we as a researcher, we think of the algorithms from the layer 1, layer 2, layer 3 and all the stuff. In the UV side, in the beamforming, that is other part of it. But we also have to tell the operator that please innovate your policies the way you want to see the network to be envisaged. So this is the overall gamut of the first 2 days of the 5G as a network actually. Here I close off. I can take some questions.
Yes, sir. Thank you. I will be reading out the questions for you. There are a couple of questions in the chat box. So one of the participants asked, is RPL TM not present in 5G?
Come again, what is that?
RPL TM mode not present in 5G.
RTM.
RPL, sir. I can unmute the participants.
Yeah,
Probably
please.
they are there. Yeah, Lavanya, if you're there, you can unmute yourself and give better clarity on the question that you have
Sorry,
asked.
sir, that is RLC TM mode.
RLC transfer. Yeah, it is still there. But what happens that transparent mode is not much innovation there, because the AM and the UM is where we have migrated the standard. But the transparent mode is transparent to the RLC. So that is still there. It is not dropped. But what I'm talking about, the 5G didn't put this head into it. They have put the head back to here actually.
Okay, so the next question is, can you differentiate the TM modes between LTE and 5G? Are they different in uplink and downlink as well?
See, the TM mode is kept on in a different mode, because why we record the TM mode is just to ensure that the RLC's invocation of the functions of the functionality is not done. So there is not much of difference between what the 4G the transparent and TM mode and the 5G part of it. So RLC's lot of functionalities doesn't get invoked once you are in the TM mode aspect of it. So there is virtually there is not much of difference between the 4G and the 5G.
Okay, so the next question is, what is the need for many different RNTs for decoding different logical
Ma'am,
changes?
just one clarity on the previous question.
Yes, sir.
Sir, I was asking about the MIMO transmit modes, not the RLC transparent modes.
Okay. Okay, let me then take it that question. MIMO TM mode, transmission mode we call actually.
In LTE, you have the TM 1, 2, 3, 4, like that,
Yes.
multiple modes for diversity and spatial
Yes.
multiplexing and so on.
So now
And
okay, sure, please.
yeah, please go ahead. Yeah.
Okay, so initially when LTE started, it has the transmission mode from 1 to 4. And as the standard evolved, we added 5, 6, 8, and 9 and all that stuff. Now, as a transmission mode per se in 5G, there is nothing called TM mode. There is only one mode. Okay, now why we did that like that actually? Because to reduce the complexity based on the TM mode. Now let me give you one. Okay, hold on. Let me clear this one to draw you what is this. Okay, so let me take it this question now. When we send from the MIMO transmission point of view, so what we used to tell the mobile saying that I have a single layer transmission, and that has been sent it into 4 such port, and please use the diversity scheme to do it actually, to do the combining actually. So this is one mode. We can tell him that, okay, please, you'll be able to see if any fading happens in any one of the link. Using the diversity combining, we're able to come out actually, the mobile can come out and vice versa actually, all this stuff. So now what will happen as the standard went actually, so we started doing the what we call as the multi-layer transmission actually. So multi-layer transmission, what we call as a single user MIMO part of it. So this is just a think of one layer, the RF point of view. But once the throughput starts happening, suppose that person has getting a lot of big Mac packet and I need a lot of throughput. So then we started inventing the feature called single user MIMO. It is already there in the 4G and MU MIMO is also there. So that means that I need more spectral efficiency and I need to transfer more MAC bits. SNR is conducive, very high SNR maybe. And I want to start the multi-layer transmission. So it means that the device will be told from the base station scheduler. The scheduler will tell the mobile saying that I am invoking 4-layer transmission to your side. So every layer will add 1 spectral efficiency. So if you have 4 layers, 4 times the amount of bits can go out to his device. Now the question is that we used to tell now saying that please switch over to the TM mode to do the SU MIMO transmission actually. So in 4G we used to tell the mode saying that now I'm going with the diversity, now I'm going with the 4G. What it got added is unnecessary signaling aspect of it. Okay. So by default by default the scheduler is doing his job because depending on certain scenario, he going with a 1-layer approach. Certain layer he's going with a 4-layer approach. So why we need to explicitly tell to do that job in the sense like now the transmission mode is at that point. So to do that one in 5G, we remove this TM mode giving the signal to the TM mode to the device. Now by inherently what we did is that now in 5G the scheduler transparently goes from 1 layer to N layer and go back to 1 layer. He can do very, very transparently, not to know it. So if he does this transparent part of it, my signaling overhead to tell to the device is also reduced because now whenever he is invoked with a 2-layer, I do just some bits that I have to enable to tell him saying that please do with this going with a 1 layer to N layer. So it has reduced my signaling overhead to tell that, okay, the TM mode is enabled now, TM5 has enabled, now TM4 has been now told. So unnecessary signaling that I have taken it out because signaling has to do first and then the packet has to go. Now the question is that if the signaling failed, the mobile is clueless, then what will happen that since I told him TM4 and it's the right time to TM5, I cannot do it actually because I have to make sure that signaling is done first. But now in 5G, we have reduced this overhead and removed this transmission mode, signaling this transmission mode, but we embedded the things with a very short within what we call as a downlink control message itself. We have put some bits to just to invoke that what is, whether it's a 1 layer or N layer, that's it. Because if it is an N layer, he directly knows that it's just like a SU MIMO has been invoked. If it is a 1 layer, then I don't have to tell, he can do his combining approach, whatever he wants to do it. Now that way also it has given me flexibility that whatever the pre-coder that has to be there, that is my digital beam wet that I talked about for the N layer transmission, that also flexibility I have now with respect to nothing to signal if I use the non-code book. Because if I have a code book, I have to do some signaling, but also I have added that multi-layer, N-layer, multi-layer transmission, non-code book, digital beamforming, no signaling. And the mobile can itself can come out actually. That I'll put into the day 3. Now, this is the flexibility 5G has given, that rather than keep on doing signaling, by some apparent means using the DMRS actually, mobile is able to by inherently come to know that the base station has invoked a non-codebook based approach or a codebook based approach. So I don't have to do it I don't have to appraise him again and again actually. So that is the part that the beauty of the 5G has come up at this point of time, where they removed this transmission mode scheme actually. Now, top of that also, what we have done it is that this is for the single user, for the multi-user MIMO. So multi-user MIMO is tremendously complex feature actually, where we are trying to reuse the same RB with a multiple users. Say I reuse the 10 RB actually in that grid. This is my frequency level grid, just put it a horizontal actually. So I can now multiplex more and more users actually. I can put EV1, EV2, EV3, and EV4, whatever I can do it actually. I don't have to tell anybody that, hey, you all are in multi-user MIMO mode, that we used to tell in the 4G days. Because the mobile is agnostic. If my digital beamforming weight is wrong or not right as per the, then obviously they will get into the interference, that the inter-user interference will kick in actually. But assuming that they are all rightly set by the algo, I don't have to do any signaling to tell that, okay, you are in the multi-user MIMO actually. Because he is totally agnostic. He knows that this is my RB, 10 RB, one precoder, I able to decipher my symbol and my bits. That's it. I don't have to make him appraise. So I reduce the whole signaling over it itself. In the day 3, we'll talk about this detail that how we do this multi-user MIMO, how we do the single user MIMO actually.
Sir, would you like to ask the next question? Is from you itself, Ganeshan sir?
Yeah. So thanks, Sapri sir. I think that's a very good explanation. My next question is that you flashed a last slide with the many RNTAs, that one for paging, one for each logical channel almost had a different RNTA number. Yeah. Just maybe you can give explanation why we need so many different RNTAs.
Okay. Now, just imagine that the identity, I didn't go into because I kept it in the day 3. This UE has many identity in the world actually in this 5G network. The core network identifies with one IP address. That we don't call RNTA, by the way, but that is not the part of it. But this network, this UE, when you get into the RAN space actually, the radio network access space, what he's trying to do, okay, his procedures to identify his procedures segregatedly. 5G has defined this whole bunch of this RNTA actually. Okay, now if you just see, I'm just drawing that procedure number 1. I want to page a mobile actually. Okay, now paging is an RRC procedure that is coming from the core network. Core network saying that I want to page a mobile. So now the question is that the mobile, when we page that, he is in the idle state actually. So I have to invoke him and with certain identifier actually, because some identifier comes when you do a throughput actually. Now he is not doing any throughput. Now how does the RAN knows that this mobile has to be paged and identified? So I'll use for this paging RNTA to do my job. Now if you see, everywhere I'm drawing my circle and my dash, it is based on one procedure that is associated to it. So this is another procedure to identify. The random access is another procedure to identify the device. The cell level, this is where when we do a transmission, the throughput is going on. That is another procedure that the scheduler is trying to identify the user. Once the throughput is gone, this is vanished. This doesn't have any significance. Before the contention resolution, we identify the guy with this CRNT, temporary CRNTA. So moment his contention is resolved,
we convert it back to the cell actually, cell RNTI actually. So it means that this procedure is completed. He has been now graduated to the cell level actually, where the throughput is been concerned with actually. Now, if you want to do a semi-persistent, this is nothing but our voice over NR use case actually. So to identify that user into the voice over NR scenario, if this procedure is going on from the scheduler, so he will use this RNTI to associate you actually, that same user. See the transmit power control FN do it. That is another feature I talked about. To identify who is the doing the transmit, I use this RNTI. So like that, if I do the MBMS broadcasting, I use another NTI. Now, if you see, this is aware based on the scenario in which I am identifying it from the RAN, because RAN is been instructed by the core network to do something, either throughput or do something. So that RAN, to identify that guy in the multiple phases of this procedure, we use this different RNTI in place. And in 5G, it has much more actually. In 4G, it was not this much actually, but because of adding up more features, like for example, we do special uplink transmission using side link channel. So for that, another RNTI is given. For that RNTI, if this user has been using uplink only transmission using side link uplink channel itself, so then to identify that guy, you use that side link RNTI to him actually. So this is the way we the RAN, the radio access or the base station knows that what procedures and what ways that he is trying to identify. He uses, when he invokes that RRC, he invokes that procedure, then RRC for that user use that RNTI to complete that procedure actually. Is that clear? Or?
Yes, sir. Thank you, sir.
So the next question which is asked is, can you suggest some book where the concepts of 5G RAN protocols and use cases are given in detail?
Yeah. So, okay. So you people have to read the book called, we all read it because to understand the things that happen. Two things I very much follow. One person called this guy. I don't know whether you heard this name. It's called Harry Holma. You search his name. So he's part of the Nokia. He has written a lot of these books, 5G and all this stuff. I forgot the title. He is part of the evolution from back from 1G itself. Now he's into the 5G. And the next is that Eric Orwell actually. He's from Ericsson. So there is a team of Ericssons that are part of it, but there are a lot of other guys. But if you think that when we go into the standard actually, so all these peoples are part of the standards actually. Okay, the first part of the Eric, where he has defined the overall architecture of 5G, that one of his essential patent actually, that he governs that how things will look like actually. Okay, so Eric's things, and he has written a book actually, and you can just check. I forget again the book names; it's not handed to me, but these are very old fellows. He's now the Bell Lab Fellows, and if you have to go through this book actually, what I have written, the physical significance of that protocol, that is the thing that why we invent a protocol actually. It's just not like that comes that today I want to invent a protocol actually, because protocol works to make the things in a harmonious manner actually. They will not talk about algorithms, by the way, because they are the person who defines the overall architecture and the systems actually. So overall architecture, how it look like and how the system will look like, that is where we have to understand the philosophy of why so many RNTS has been there actually, why this, why that, why this protocol has been invented actually. So all these things they will talk about, and it's a good book to read actually. Algos, they don't get into the algo part actually. So algo is separate activities.
Those were the only questions, sir. So if any other participant has any other question, you can unmute yourself and ask. Okay. So looks like there are no further queries. So thank you very much, sir, for the detailed talk of your session 2 on 5G. So it was really very elaborate talk. It was very nice. So hope the participants could get the details of how the concepts are used in 5G. So we would like to see you in the next session, which will be on October 23rd. So thank you all for joining. Thank you,
Yeah,
Saptarushi, for
next
sparing.
session will be a lot of mathematics will come, a lot of algorithms that I talked about. I'll start giving the glimpse of it. So please join in the third concluding session.
Yeah, so there is a break of 1 week, so it will not be next week, it will be that coming week, which is October 23rd. Thank you, Saptarushi sir. So thank you,
Thank you very much.
participants and other Exicom members who are there in the meet. Thank you all.
Thank you, sir.